upcoming book. So we actually just signed a deal with the O'Reilly Media folks. We're working on a book.
So as you can see here, we're super excited. We're gonna start writing, and we actually started already, writing a book on data science on Amazon Web Services. It's currently targeted for an early 2021 release. So the good news is that we're super happy to hear about feedback from you. So if you want to give us a little bit of like your feedback, what you would like to see in the book covered, if you go to data science on aws.com, and Chris can post the link to the chat window, you see here on the website short introduction of the two of us, but more interestingly, 2 links. So you can see here a link that takes you to a short survey, and you can actually provide us here with a little bit of insights, a little bit about yourself, like which roles you're working in, but also what topics you would really like to see in a book like that covered. So if you have some extra time, maybe, and would like to see such a book, we're super interested in hearing about what you would love to read. Give us a little bit of your ideas, what tools you're using, what use cases you're interested in, so we can really make the book as relevant as possible. So this is the feedback survey, and you'll also find a link to our Git repo here. So this is work in progress. So we started already showing a couple of good code examples here, but if you find something, a couple of the repos might still be empty. So it's, as I said, work in progress. We will working on them and produce content over the next couple of weeks and months. So feel free to check in regularly if there's something you're interested in seeing in here. You'll also find in this repo, if you look into Kubeflow, the notebooks and the content we're running today in this workshop. So we will just clone that in a little bit in the part here in today's workshop. And yeah, that's about the book. We're super excited, and you can help us providing feedback.
Cool. Okay. So yeah, and a couple people are sending me directly their emails. Please actually take the survey. It's just a quick, I think, 8-question survey. Put your email in SurveyMonkey, and we will then add you to the list. So yeah, glad you guys are excited. We spent the better part of the holidays actually not spending time with our families, but spending time with the O'Reilly family, trying to figure out the best content to put in here. So super excited. All right. There, I think everything's good to go. Ansha, do you want to start? I'll send the link to the material, to the workshop material. Okay, so let me send the link to the actual workshop material. The link is here, coming. Okay. All right, so that's the link to the actual material. That's what Ansha has up on her screen right there. Yeah, Ansha, do you want to kind of kick it off here?
Yes, sure. So once you get to that link here that Chris posted in the chat window, you should see here this environment that I'm also sharing on my screen right now. And this is basically the instructions for the whole day. So just make sure you're getting to this site, and then once we get you onboarded into the AWS accounts, you can then follow us. So we're going to show you what to do, and we're going to guide you through, and then we give you a little bit of time to do the single exercises. But you can basically follow through here. So what we start to do here really is giving you a workshop that introduces kind of an end-to-end machine learning pipeline. We're going to show initially how to work with AWS SageMaker, and then we'll also do EKS, so that is the Amazon managed Kubernetes environment, and we're going to show and actually also install Kubeflow on EKS and have a lot of good examples. So by the end of this workshop today, you'll be hopefully able to do exactly that. So build an end-to-end machine learning pipeline with the tools I've just mentioned. We'll also touch on doing distributed training with the environments. So you can play around and see how we can actually set this up. And we'll also describe a couple of different approaches here. So in the first part, we'll talk about a little bit how to use Horobot as a distributed training framework. And then later on, we'll also move to SageMaker and show you how you can do distributed jobs there, and also how to do distributed training on Kubernetes by Amazon EKS and in Kubeflow. So some of the exercises today will use GPUs, so we can also see training being executed on GPU environments. So it's hopefully an interesting content for today, and hopefully you learn some good things here. So before Chris shares your logins here, let me just quickly touch on a couple of first things here. So when we look at typical machine learning development workflows, there's basically two stages where you can benefit from scaling out from distributed and parallel experiments. So one is really what's defined here as parallel experiments. And this is when we train different models running in parallel to find and identify the best model. In contrast, when we talk about distributed training, it's normally distributed training of a single model to be able to train faster. And the focus of this workshop today is really the distributed training of a single model. So in general, challenges with that approach when we try to scale the machine learning. So when we're basically starting to get off our laptops and want to really train in a bigger environment and scale out, a couple of the challenges is that the setup doesn't always translate, right? So it might be working very well on a laptop, but you might have different software dependencies, etc., when you move to a cluster environment. And you also have to think about the infrastructure management, right? So those are often big challenges. And one way to address those is, for example, for the software dependencies, we want to use containers, right? Containers really give us this packaging where we can bring together the training code, all of the dependencies, and the configuration, and really get kind of a lightweight, portable, scalable, and consistent environment. So once we package everything, our code, the dependency, and the config in a container, we can then basically bring it into a container registry and pull it out on the clusters, right? And it's really helping us to scale. So on the second point, infrastructure management, this is really where managed services can help, right? So looking at a cloud environment, you have the compute, so you can go ahead, obviously, get compute instances, and then start building up your environment. Or if you don't want to think too much about how to manage that infrastructure, you can also leverage managed services, for example, for containers, right? So in the Amazon AWS world, this is, for example, called the Amazon Elastic Container Service, where you can bring your containers and deploy. Or if you want to use Kubernetes and you don't want to bother too much with setting up the whole cluster and maintaining the environment, there's a couple of options there. And EKS is the Amazon Elastic Kubernetes Service, where Amazon helps you to run the control plane, and you're really just taking care of your worker nodes and deploying your pods and applications. And then there's also higher level services. So specifically, if you're looking at machine learning environments, again, at Amazon, we have Amazon SageMaker, which is a fully managed service that helps you to really bring together all the tools, the APIs, the services you need to build, to train, and to deploy a model. And it has built-in functionality around hyperparameter optimization, really easy to scale, like from maybe train on a single instance to a couple of instances, so go to distributed training, and also helping you in terms of the underlying infrastructure management, so you don't have to think about how many instances do I really need. You can leverage something called auto-scaling groups, which then, based on the workload, scales the underlying infrastructure to address all of the needs. So there's a lot of good things with cloud services that really help you to bridge that step coming from a notebook environment and going in a distributed production scale. All right, quickly here on distributed training, there's also different approaches. One is the asynchronous, one is the synchronous. And basically, when you do distributed training, you still need kind of a central authority that keeps track of, for example, the weights in the training runs, right, and readjust. So when you do the asynchronous, we're basically propagating the information, but don't have to wait for everyone to receive the information before to move ahead, right? In the synchronous world, this is exactly what we're doing, like in this example here with the ring all reduce. So we're getting the results from the training runs, and then we're propagating back the weights, and all of the instances basically need to receive an update before we can start the next run. So this is a little bit on the asynchronous and synchronous here. In our first examples that we're doing here in part 1, we're using Horovod. Horovod is a pretty popular framework to do distributed deep learning. It supports multiple frameworks, TensorFlow as well included, and it's actually using this ring all reduce and something called the message passing interface, MPI, which is coming from the HPC community to do that message propagation. And yeah, that's, I guess, a little bit here for the introduction part. So let's see how we are with getting ready with the accounts here.
Yeah. So next up, okay, some people are asking if they can use their own AWS accounts. My comment there is you can, however, we cannot support you. You know, that would be the equivalent of saying, can I do this on my own laptop? And I have no idea what's on your laptop. And when, you know, yes, many years of training, I've realized the best way to keep the entire group, and like specifically large-scale training like we're doing here, we need to keep people on Rails, and the best way to do it is with the environment that we're about to give you. That said, everything is open source, HPS, github.com/data science on AWS/Kubeflow. You can reproduce another time in your own environments. But for today, I ask that you stick with the environment that we're just about to give you. We also have set up GPUs for you for this environment, and lots of times you would need to actually submit a ticket to increase limits. We've already done all that for you, so please just use the environment today, and then you could try to adapt it offline. Okay, also you can certainly download any notebooks that you have modified that are not in the open source repo, or just that you've modified. You can certainly download those and then, you know, yeah, copy them anywhere. All right, so I'm going to post a link here, and you guys will be able to get to spin up your own environment. Here it comes. Please just click this once. We only have a limited amount. We have just above the number of attendees, so please only click this once. Please don't share these with your friends. We need everyone that's on this workshop to be allocated one instance. Grab the HTTPS link and put that in your browser. And that should take you to a screen here Site can't be reached. Are other people having problems? I just switched over the DNS, so it might be. Okay, hang on one sec. Okay, yeah, DNS hasn't propagated yet. No problem. I have the other link here that's ready. It'll be this one. That one. Coming soon, 1 second. Didn't work either. Okay, 1 second here. Okay, got the new link. Yeah, the link will be HTTP. It's just a quick link that I stood up for the purposes of this. It's not HTTPS. Try that link there. Again, please only hit that link once. Do not click refresh. Don't paste your link here, or others will potentially grab it.
All right, so once you get to that web page and you get that allocation link, you can use the link provided, and then you should see and come to this website as I'm showing here. So we're just making sure everyone reaches that point.
Okay, for those of you having issues, just ping us and we will allocate you a server here manually.
So the rest of the folks, yeah, perfect. So
yeah, team dashboard's good.
Yeah, team dashboard. So I'm going to put in my hash code for today here, accept the terms, log in, and then exactly, you should see this team dashboard here, which I'm showing. And you can click then on the AWS console. Make sure, in case of you've been working in another AWS account before, that you're logged out of everything from corporate, from personal accounts on AWS before. Once you've done that, put in here your hash code, team dashboard, and click on AWS console. And then just, again, use here the open AWS console link. And this should bring you to a fresh AWS account that we're using for the workshop today. And you can check on the top right here, make sure it's not your personal or corporate AWS account, but it says team role / master key. So by this, you can double check that is the provided account we're using here today. And also make sure you're staying in the US West 2 Oregon region. This is the region we're going to be using for today. So please don't change that, otherwise some of the resources might not be available there. So make sure you're staying in US West 2 for the day.
Here is the allocator link. It's HTTP, not HTTPS. The link in the JSON response from that allocator link will contain an HTTPS link. Follow that link, HTTPS link. Okay, for those of you sending me errors, tell me where you're seeing the error. Which link are you having problems with? The allocator link? Okay, so we got to fix a couple people here, no problem.
Okay. A couple of you are in, a couple of you are...
Okay, Richard, I'm going to send you a link. 1 sec. Okay, we're still allocating for those that we're having problems. Also, make sure you're logged out of any firewalls or anything goofy like that. Any VPNs running locally will have lots of problems. You won't be able to do the workshop if you cannot. You typically cannot get to the workshop if you can't get to this point. So, all right. So let me go back through. So Edwin's good. Copying link from JSON. Yeah. People are reminding me to say that when you go to the allocator link, the response from the allocator link will contain another link that has the link that you need. Okay. Looks like Kenro, you're still having problems? Okay, Kenro, I'm sending you a link. Okay, Edwin, Kenrio, Pavan, are you still having problems? Okay. All right, so for those of you having problems, please send a note directly to just the panelists this time. Whoever's still having problems. And for those of you that are okay, please don't type anything in the chat right now.
All right, so Chris will take care of those who still need to access. I'll go ahead a little bit here, no worries, just to make sure everyone else can start doing something here. So I'm gonna show the console here on the right. Again, make sure you're seeing the team role / master key on the top. Make sure it's the provided link from today, the account. And what I just did here, I put the instructions here on the left window. So we can follow along here live. So,
one sec. For those of you seeing invalid hash, make sure you get rid of the space at the end. Make sure there's no spaces around that hash. Trim it manually. So, okay. I'm still addressing everyone that's sending just the panelists a note that they're having problems. So I'm still getting to everyone.
Yep, Chris is on it. All right, so if you go to the instructions here, getting started section, you can basically follow along, right? So what we just already did here, and hopefully get everyone online here in a bit, is logging out of all AWS consoles, log into the workshop portal, so you find the dashboard event engine link in here again. You should see either here the screen with a hash, or you go directly here to the team dashboard. Just click on the Open AWS console. Make sure you're staying in the US West 2 region. And then we can go to the next step here.
Okay, let's pause for a sec. I just want to make sure, because there's actually more people than I thought that are having problems, and I don't want to have to redo all this. So for those of you that are okay, just kind of sit tight. Yes, okay, so once you get to the dashboard, click on AWS console, but hang tight here. Okay, so I think I got to everyone. Anyone still having a problem? Okay, so Sangeeta does not see the documentation on the left-hand side. So Ansha has her screen split into two different screens. Once again, a link to the material that's on the left side of her screen is here. Left side of Ansha's screen.
It's just a second browser window I opened here and put to the left.
It's a second browser window, yeah. And it has a link to the workshop.
It's really just for convenience, so I can have the console here to the right and read through and show the instructions on the left. So you can have a separate tab or also like arrange the windows.
Okay, one last call. Does anyone have any problems getting into this environment? Okay, Musumi, you have the wrong link, please. Please use this link, not eksworkshop.com. We've made a lot of improvements, or I guess, customizations to EKS Workshop. And here's a link to the data science on AWS.com. Cumming O'Reilly book. We have to move on, guys. Just send a note right now if you cannot get to what Antje has on both the left and the dashboard, ultimately to the AWS console on the right.
All right, folks. So on the right, as I said, it's just another browser window showing the console I logged in, and on the left is the instructions. So hopefully the majority of you are at this stage right now. So as a first step, we will be using a Jupyter notebook to run most of the workshop examples today. So we will be using Amazon SageMaker, which also provides us with a hosted Jupyter environment. So this is the first step we're doing here. So we're launching it. If you go to the console and then search for Amazon SageMaker, go to SageMaker, and I'm just gonna quickly maximize this view. So if you're logging in for the first time here, you see this splash page here, welcome to SageMaker. On the left side, you see a notebook, and click on Notebook Instances. And here, you can create a new notebook instance, and this is what we will be doing. So I push that window here to the right again to walk you through the settings here. So once you are there, create notebook instance. We're giving it a name, and you can basically copy the values here from the instructions. So call the notebook instance workshop. And also for the size of the notebook instance, we need a little bit bigger instance. So we selected here a T3 X large. And then if you click on the additional configuration, we also increase the volume size because we're going to pull down a couple of data sets. So make sure you're also increasing the volume size here attached to that instance to 50 gigabyte. And you see the instructions here on the left again. If you follow through those, you see here notebook instance name workshop, instance type a T3 X large. In the additional configuration, give the volume size an increase to 50 gigabyte. And then we're also selecting the team role. I'm just checking quickly with Chris. We played around yesterday with those.
Yep. Yeah, everything is up to date.
Okay, perfect. So we're sticking here. So the IAM role is basically setting the permissions, what our Jupyter instance we're creating is allowed to do inside of the account, right? So this is the identity and access management settings in the AWS cloud environment. So here's the role that is pre-created for us. It's the team role. So just keep that. And then we're good to go. So we can hit the create notebook instance here on the bottom right. So this will show then a pending state. So the instance is being created, and Amazon SageMaker will deploy the hosted Jupyter environment for us on that T3X large instance we selected. So just give this maybe 1-2 minutes while the instance is being created, and then we're able to log in here. So as soon as it's ready, it will show on a status here. It will switch from pending to in service and show you the links to open it. So just give it 1-2 minutes here for it to be ready and started. So mine is still pending. It will take 1-2 minutes, so be a little bit patient here. Should be up here in a bit. And then what we're doing next, as soon as the instance is ready here, we'll also update the privileges. So in general, you would want to keep all of your services and the components you're working with here, the least privilege access, right? In this case, because we're going to use the instance later on to also spin up our Kubernetes cluster and do a lot of things, we'll actually attach an administrator access policy in a bit here. But general rule of thumb, obviously, is always give the least privilege that is needed. So make sure you're hitting the refresh here to make sure it's still in pending and to see when it's ready. And it's just a couple of more steps, and then we're ready to git clone the content and get into the code examples here. So in the meantime, I mean, you can click around here a little bit maybe, not to just stare at that window. So I just maximize here my screen again. What you can see here basically on the left are a lot of like the different components that Amazon SageMaker actually provides you with. So we're currently in this notebook section here, but basically there's a service, for example, called Ground Truth, which will help you to label data. So this is targeted if you have a large set of data and you need a service that helps you label those. You can either use private workforces or something called the Mechanical Turk from AWS, which is basically a worldwide workforce that can help you achieving that job. So you give instructions, for example, if you have like a large set of images and you need to label, I don't know, identify certain objects in the pictures or identify maybe, I don't know, a sports, whatever you want to do. You give instructions and provide the data set, and the workforce or even a private workforce can then help you labeling data. Also later on, we're going to show the training jobs. So there's also a section here for training jobs. So we'll start a couple of those in just a bit, so you can also see them coming up here. And similar for the inference, so once we deploy models to production, you see here endpoint configuration and endpoints. So we're going to come back to this console in a bit here later and check out the different functionalities that SageMaker provides. So going back to my notebook instance, I just saw it flips to in service. So have a look again at your notebook instance screen. So you see here on my screen, as soon as it turns green and says in service, it's ready to connect. And then you have here on the right 2 links, the Open Jupyter and Open Jupyter Lab option. So in our case, we're going to click on the Open Jupyter. Oh, by the way, I need to, first let's change the roles here. So before we actually click on that, go back here, click on the name of the notebook instance, workshop, and this will show you the details, the configuration details of that notebook instance. And once you scroll down here, you see this IAM role, ARN. And we're going to click on that and attach an administrator access policy, so we're able to use that instance later to do also the Kubernetes tasks and things. So we click on here, and this opens a new tab, which brings us to the IAM settings. And here we can go down and click on Attach Policies. And if you miss one or the other step, you can always follow the instructions here on the left. It details exactly what you need to do. So in this Find Policy, we just type Administrator Access. It's also the one shown on top here. We click on that policy and say Attach. Okay, so click on your notebook name. It brings you to the details. Scroll down to the IAM role as shown here on the left. Click on that hyperlink. It takes you to the Identity and Access Management console. Scroll down, click Attach Policies. Look for the administrator access, select that, and click on Attach Policy. So it should show up here then as part of this team role. All right, so with this, we basically gave our notebook instance administrator access, which again, you don't want to do like in a normal environment. Make sure you're only giving it the least privilege. For this being a workshop purpose here, and we're doing a lot of things from this notebook, it's probably the easiest way for today to not run into any issues. Okay, so once you've done that, you can basically close that window again and click on your notebook instance. Just hop back here. Click on Open Jupyter. And this should then bring you to this fresh environment, a hosted Jupyter environment here running on that instance. And I'll just do a quick check here if people are following. So just a quick walkthrough here. If you're in the console, go to Amazon SageMaker. You create it. No worries. If anyone is behind, just have a look at the instructions here. I do a quick recap. So we went to the console, searched for Amazon SageMaker, which is the hosted machine learning environment. We clicked on Notebook Instances, and we created a notebook instance. So click here if you haven't done that yet, create notebook instance. And in the instructions, you find the details to put in. So give it a name called workshop, select the ML-T3X large instance type. Increase the volume size to 50 gigabytes because we're pulling down a little bit of data later on. Keep the team role selected in the permissions and encryption here, and basically hit create. It will take 2-3 minutes. And then we'll also click on that instance that we named workshop. If you have it called differently, it should be okay. It should not bother us too much here.
One quick note, some people accidentally close their tab. Make sure you copy the link that came out of the allocator. I just shut down the allocator because we ran out of instances, so there's no more instances. So don't lose that link that came back from the allocator. Okay, so put that into your copy buffer somewhere in a text pad. Richard, I don't quite understand your problem. Send me a note directly with every piece of info that I would need to debug this. It's not registering with me. Okay, Benny, make sure you put in your old link that you've got from the response from the allocator like initially. And for those of you falling behind, I've pasted the link to the documentation a bunch of times. It's the one that says master. I'll paste it here again. Okay. I think 1 or 2 people might be reusing the same accounts. I don't have a solution for that now because we did run out of instances, so just do your best. Create your own, find it in your browser history. Not the allocator link, that's been removed, but you can find the link to that has that hash in it. All right.
So you all should have created the notebook instance in the Amazon SageMaker console with the settings that are described in the instructions, right? We then clicked on the name of the instance. I called mine workshop. The majority of you should hopefully also call it workshop. If you put another name in there, it shouldn't matter too much. Just for the sake of having the same names here, it makes life easier. If you scroll down on those settings page, the configuration details, you find under permissions and encryption an IAM role RRM. This is the link to our role that gives the permissions what the instance is allowed to do. If you click on that, it takes you to those settings with the policies. And what we've done, we clicked on Attach Policy. In my case, it's already attached, but you looked for Administrator Access and then attached that one. So I'm going to cancel. I have done that already. And it should show up here in the list of attached policies, right? So this is giving us this instance actually an administrator access. So this is what we've done so far. And then once you've done that, you can basically click on the Open Jupyter link and go to your Jupyter environment. So here you see the links. Click on Open Jupyter, and it takes you to this Jupyter environment. And then we're almost good to go to jump into the code. So make sure you're following to this step. If you fall behind, as said, just check it out in the instructions here. It's every step is outlined here. All right, so we created the notebook instance. We updated the IAM role to give administrator access. And now we're going to clone the Git repo so we have the notebooks and all of the code we need for the rest of the day. So what we're going to do is here in the Jupyter environment, we click on, let me increase this here. We click on New and start a new terminal window. And then you see here in the instructions, we do a git clone. And a little trick here, so in the instructions in the top right corner of each code box, you see a little copy icon. So you can just click here actually, and it copies the content into your copy buffer. So you can click here, copy to clipboard, and then basically you can paste it right away in your Jupyter terminal that you opened. So what we're doing here, we're jumping to the SageMaker directory on this instance, and then we're git cloning the data science on AWS Kubeflow Git repo that has all of the code and the notebooks for today.
Yeah, that's the exact same repo that I sent earlier.
So you can do an ls command to make sure it actually pulled everything. So we're seeing here part 1, 2, 3, so that looks good. So again, go to the Jupyter, open a new terminal window, and go to the SageMaker directory as in the instructions shown, and run that git clone command. If you go back then to Jupyter, you should see this Kubeflow folder popping up then. And if we click into there, there's the code for today, and you see a folder called the notebooks. And this is basically what we will be using here in the next steps. So make sure you open the terminal, you git clone the repo. Just checking here if everyone is catching up. So the git clone command, go to your instructions here. You should have probably the instructions maybe here on the left as I do. It's making life a little bit easier to just follow along. So it's in the instructions, download the workshop content. Again, there's a little icon in each code box here, the top right icon. You can just click that, and it copies the code shown into your clipboard. So that's a very easy way, so you don't have to manually select. Copy it in your clipboard, and then you can paste it in the terminal window.
Okay, yeah, some people are asking where the git clone command is. The git clone command is in Ancha's screen that's being shown right now on the left. You have to be inside the terminal within Jupyter Notebook. Okay, can't see the administrator access and the policy. Ansha, can you show the administrator access?
So if you click again, here I'm back in the, let me make this bigger here. If you're in the SageMaker console, here is the notebook instance you've created. Click on that. You see the details. You scroll down to IAM role. You click on that. It takes you to the IAM management and permissions. And depending whether you already have attached it or not, if you click here, policy names, click on show to more, I have the administrator access policy here. If you don't see it in here, it's not attached, then click on attach policies and look for administrator access. It doesn't show up in my case because I already attached it. If you haven't done that, it should pop up here. I think it's even the first one that is shown. Make sure you're selecting this administrator access here and then click on Attach Policy on the down right. Double check here on the screen that it shows up.
Yeah, so to verify, make sure that the team role has the administrator access right where Ansha's cursor is.
All right, so this should hopefully bring everyone to this one here. So again, I'm back in Jupyter. I did my clone command. And this is basically the first setup. So hopefully everyone is close at this step. And we can jump in with the first part of the content for today. So part one is doing single node training. I'm just checking with Chris.
Yeah, I'm going to launch a poll here to make sure everyone's, I don't want to jump into this unless everyone's there. Well, not everyone, but most of the people there. So let me know that you're good. If you're a bit behind, select that. If you're lost, select that. If you're just in horrible shape, select that and ping me. So I'm getting lots of questions on where the instructions are. The left side of Ansha's screen is this. The right side is the workshop that we gave you earlier. Okay, so it looks like most people are good. Close to 90% are good. So I think we're going to keep moving ahead. If you're a bit behind, just continue to follow what's on the left. Okay, for this workshop, ignore any and all warnings. We are demonstrating bleeding edge tech and there will be lots of warnings. So someone's asking, and please send these notes to all panelists and attendees. So Levi, please change your thing to all panelists and attendees. So Levi's having a problem when running source activate, which did we get to that yet?
Not yet, no.
We have not gotten to that yet. You will see a warning about GPU. Ignore that. Just keep moving. Okay.
All right, great. So the majority of you are good. That's perfect. So let's move on here. So part one, we're going to do a single node training with SageMaker. So this is really kind of a very easy start into the topic. We're going to walk you through training a TensorFlow Keras model in the notebook on a single instance. So we're actually using this instance that the notebook is running on. And then in the second step, we're going to change the script and then show you how you could apply changes to basically be ready to run this in a distributed environment. All right, so the problem statement, we're going to use a single CPU training script to first do a single instance training and then prepare the script to do a multi-node distributed training. For the frameworks, we will be using TensorFlow, Keras, and Horovod in this example. And as a data set, we're going to use the Cypher 10, which is an image data set you can see here. Quick sneak preview. It's consisting of 60,000 images with a size of 32 by 32 pixels. And it's categorized into the 10 categories you can see here. So from airplane, automobile, up to truck. We have 40,000 images for training, 10,000 for validation, and for test. So this is going to be the data set we're going to use in this one. And it's not a very big data set, but again, it's showing the idea how to do that. And then obviously, this one could run on a single instance, but you're going to have like more difficult problems. You want to see how to do this distributed. So let's do this. So we're going to prepare the data set. So first, we need to download that. So if you see here in the instructions, this is again a terminal command. So in your Jupyter, probably it's easiest to just keep that terminal window open as well. Let me do a quick clear here of the screen. So I can again just copy the whole cell by clicking on this top right icon here. So I do that and paste that to my terminal window. So what we're doing here is we're going into the SageMaker Kubeflow notebooks directory We're making sure we're in there. We're then starting a Conda environment for TensorFlow P36. And then we're going to run a Python script which basically downloads our data set and also splits the data set right away in the training, test, and validation. We're defining an S3 bucket we're going to use for the rest of the workshop. So this is going to be created here. And we also, whenever we create a variable like the S3 bucket here, we're also exporting that to our bash profile. So in case we need to pull in that information, and we actually do have to do that in a couple of places later on, we can just basically call the environment variable we're setting here. So this is what happens. Then we create the bucket of this S3 name we're creating, and we're syncing the data set to the S3 bucket. So it takes a little bit, as you can see here on the right, creating the Conda environment, running the Python script, and then syncing the data. So once you see completed being echoed here, the script has run. So check for any errors, but this should run smoothly. Warnings, as Chris mentioned, you can ignore the warnings. There's always tons of warnings using those libraries and things. So as long as you don't see an error message, you're good. Okay? So I'm just checking my code here. It looks good. And we're ready to go to the next step. So this one we're going to execute as a Jupyter notebook. So we're going to go back here to our listing, and we're going to click into the part 1 Horovod folder. And here you see 2 notebooks. So the first one we're going to run here is the single instance, Cypher 10 single instance notebook. So click on that, and this opens up the Jupyter notebook for this exercise. So I'm going to go here and maximize this screen. So the rest of this is really like executing this Jupyter notebook. For those of you who are not familiar with Jupyter, we sometimes have people that don't know the environment. This is basically kind of an IDE to develop your machine learning code, right? It has instructions in here, so please feel free to read through it. So here we're doing the single node training on a local instance. We're pulling and using the Cypher 10 dataset, which we just push to our S3 bucket. And we're going to do the local training here on this instance. You can see here the code, and the majority, I guess, is familiar with Jupyter, but again, for those of you who haven't used it before, those are executable code cells. So you can just go here and either click Run, or you can do a Control Enter command. And once you see here this star in the cell, and the star means it's executed, and once you see a number popping up, it means the cell has been executed. What Chris just got nervous here about, you can also do, if you want to do it quick forward, click Shift Enter, and that takes you straight to the next cell. So you can do one by one, or just do a quick run through and then read what happened. So in this case, I'm just going to guide you a little bit through what we're doing here. So in the first step, we're importing the essential packages. So here you can see we're importing TensorFlow, a couple of OS libraries, a bunch of TensorFlow Keras layers, models, optimizers, and callbacks. And we're also defining some data characteristics like the height and the width of the images, the depth. So we have 3 color channels. We have 10 classes, as we've shown before, and the number of trained, validation, and test images here. Then in the next step here, we're defining some functions to actually do a little bit of data pre-processing. So for example, in the pre-process, we resize the image, add some extra pixels, randomly crop an area from the picture, randomly flip the image. So it's really just helping us to do a little bit of data pre-processing. We're also having a function here to create batches. So we're passing in later the images in mini batches. And so just run this cell, click Shift Enter. Again, make sure shows the number here. And then in the next step, we're defining our hyperparameters. So we're setting the epochs here. So we're just going to do one epoch. Don't go too crazy because this is going to be executed on that T3 instance you're currently on. So don't go too crazy here, otherwise it will blow up the instance. Keep it to one epoch here. You can basically pretty much keep those values. So learning rate, batch size, momentum. We're using the S2D optimizer, defining a checkpoint directory, also pointing to the training evaluation directory where to find the data. So let me execute this one here. Again, some warnings here from TensorFlow, you can ignore them. We're then defining the model. So we're creating this model here, passing the learning rate, the weight, decay, optimizer, momentum, defining the optimizer object here. And then we're ready to compile our model. So we're calling the model compile. And then we're ready to train. So we're doing the model fit in the next cell. And you can see that we're passing here the training data set, the X and Y, the epochs, batch sizes, etc. So the training has started. And you can see here it's taking a little bit of time. So make sure you're not going like to 100 epochs here by accident. So we're running one epoch here on 312 samples. That's the batch size we're doing, and validate on 128. So this will take a couple of seconds here. You can see the progress. And then as a last step here, we're basically scoring the model and see how we're doing. All right, go here to the right. Checking on the chat if people are following.
Yeah, someone's asking about the word epoch. Yeah, epoch. One epoch is one complete cycle, one complete traversal through the entire data set. So the idea is you have a training data set, you want to run through it and calculate and try to fit your model to that data set. And typically you want to go through the data set multiple times, and you're typically shuffling that data set each time that you go through. And there's very easy ways, there's flags, shuffle equals true. This is supported by all the frameworks to shuffle the data so that the model sees the data in a different order. That's very important if you're not doing time series. If you are doing time series analysis, you need the order. The model has to learn the order. So just the simplest way is just think of an epoch as one complete pass through your data. Typically, you would want to do 4 or 5 of those. We don't have enough compute in this notebook to do it, but we will do it later when we actually do this in a cluster. As Ansha said, this is training inside the notebook instance, which is a T3, which is relatively small. We do that on purpose because you shouldn't be doing large-scale training in your notebook. And we'll show you how to do it on the cluster on both a SageMaker cluster and then later the Kubeflow cluster that's running on EKS.
Yeah. So my model training has just finished. You can see here, took roughly here 5 minutes. So I executed the last cell here as well to evaluate the model performance. So we're printing the loss on the accuracy, and you see it's not doing pretty well here, but we had like really few images in one epoch, so not a big surprise that we just have here the accuracy of 30%, but we're going to do it a little bit in a distributed, bigger way soon. So hopefully you followed along the steps, right? So a very easy example, we pulled in TensorFlow, defined a couple of data pre-processing functions here, and then defined our model, set the hyperparameters, pointed to the data set, and basically compiled the model and trained the model. Boom. So pretty straightforward, right? As a next step, we want to prepare that script to basically run distributed. So we move on to the second notebook in that folder. So we're now doing the converting this training script to use the Horovod API. So if you go back to the folder here in part 1 Horovod on the Jupyter instance, We've just run the single instance. You can now click and open the Horvath notebook. And I'm going to go here again to full screen. So in this exercise here, we're going to use the same code, but we change it to actually use the Horvath API. And this is really kind of to prepare for the distributed training. So in the first step here, we import Horvath. You see here the import Horvath TensorFlow Keras is HBD, and also the TensorFlow Keras backend is K. Pull in a couple of libraries again. It's pretty much the same code from before in that part. We do have our data preprocessing functions here again to resize, crop, and flip the image, make the batches. So that's the same code. We still have here the hyperparameters, so we're still sticking to one epoch for now. We're still on our notebook instance. We're going to just use that. A change we're doing here, we initialize the Horvath and get the size of the cluster. So this is the HBD init command we're running here. We're querying for the size. In this example, it's literally just a single node because we're still on our notebook instance. But this is also how it would detect, if you have a couple of instances running to perform this job. We're pulling in configuration and passing the session here. Get the model again, passing the parameters like before. One thing we're doing here to adopt for distributed training is when we define the optimizer, the SGD, we're actually scaling the learning rate by the size of the cluster. So the change here is that we're using the learning rate and multiplying by the size we just queried here above. So in our case, it's still a 1. If we have a couple of instances or workers to perform the training, this would basically scale our learning rate then. Then as a next step, we convert the optimizer for distributed optimizers. So we're pulling in here the HVD Horvath distributed optimizer that takes care of this distributed training process. We're then doing the model compile, giving callbacks to actually, again, capture the metrics and stuff, call the model fit, and let's actually execute this. So let me run through here. Should be pretty straightforward. So again, the model fit will take 3-4 minutes here to run. And with this notebook, we now changed our training script and the code to be ready to be distributed, right? We're not yet doing the distributed training. We're still on our single instance, but we already prepared and made changes to the script to be actually ready to put that on a distributed environment. So let's just give it a little bit of time here to finish. It's not going to be a dramatically different result as we're still doing it on the single instance here. So let me put that here to the right again to have a look. And this is basically the first part, right? So we've been using the SageMaker notebook instance with the Jupyter notebook here to actually do some ad hoc training, right? So this is really when you first get hold of a data set and you're doing the first couple of maybe a little bit of data pre-processing here ad hoc, trying to play around a little bit with the values and preparing for the distributed training. And then in section 2, we're getting a little bit more into at scale, and we'll be using this to actually do it on a distributed environment. So my notebook is almost done with the training. Let me check on the questions here. I think Chris got it covered. All right, so my training job finished here, the model fit. As I said, it's pretty much similar scores to the one before, so 28% accuracy, 29. Not too exciting, but again, it's just a small set of like 312 samples in one epoch, so we're not taking too much note of that accuracy for this one here. Okay, perfect. So we are ready to go distributed. So actually, you can go ahead and close those two notebooks if you want to. And we're going to jump now into part 2 of the workshop. So the first parts are pretty straightforward. We're now going to use Amazon SageMaker in this part 2 to do distributed training. And let's just jump right in there. So if you click on the notebooks and you open up part 2 SageMaker now, and click on Horvath, you can see here another notebook which we're opening. And in this case, we have the code, the notebook, and we're going to use SageMaker to basically help us in the instance, in the underlying infrastructure management to do a distributed training. So we're going to use the script we have. We're going to pull a training container that gets loaded with the script and access to the data set residing in S3. And then we're spreading that container and launching a couple of instances to run our training job. So let's go ahead and open this notebook. So again, we're in part 2 now. So if you go to your Jupyter Notebook instance, you can go ahead and close the part 1 notebooks, jump to part 2 SageMaker, Horvath, and open the Cypher 10 SageMaker distributed notebook.
It's important to note because there's a couple people seeing a learning rate keyword error, unexpected keyword. We saw this last night while preparing. We just reran both notebooks and it seemed to go away. You don't have to run those notebooks to continue on. So worst case scenario, if you're still seeing it, just keep moving ahead. There's very little that depends on previous stuff right now.
Yep, correct. All right, so let's jump into this part 2 notebook here with Horvath. So what we're doing here, we're actually now using the SageMaker Python SDK to issue training jobs to the SageMaker environment. So we're basically jumping off our local instance here, which could be also like, a simulated local laptop, etc. And now we're going to jump to actually leverage the cloud environment, and we're using all the goodness of the infrastructure management and the scale-out possibilities we have here. So in a first step here, again, we're going to import a couple of packages we need. You notice here we're importing SageMaker. That's the SageMaker Python SDK. And we're going to pull a couple of settings here through the SDK that we need. So one is, for example, we're pulling the current session information through SageMaker. And we're also pulling our execution role through this command here and the default bucket we will be using. So run the cell, pulling that information through the SDK. And then in the next step, we're going to specify the hyperparameters. But in this case, we're also specifying the instance types and the number of instances we want to run the training job on. So this is now using GPU instances, right? So we want to have some fun here in this workshop. So we're going to increase the hyperparameters, as you see. So we're doing 5 epochs, learning rate, momentum. I think the rest is pretty much similar. We're increasing the batch size here. And the instance type, we're selecting here an ml.p3.2x large. And that's the AWS instance family, the P3s that come with GPUs. So we're going to use 2 instance count 2 P3 instances here to do distributed training. So execute the cell here. So again here, for a summary, distributed training with a total of 2 workers, 2 instances, and we run 1 Horvath process per host. So exciting. So as a next step, we're going to create the SageMaker estimator by passing all of the information needed. So because we're still using Horvath for the distributed training framework, we need to define a couple of parameters here. and also this message passing interface, which Harvard uses. So it starts by pulling TensorFlow through the SageMaker API now. So we're importing TensorFlow through SageMaker. We're giving it the path of the output path, where to write the information, the results. We're just constructing here a job name. So this is taking instance count processes and a timestamp. This is just a name. And we're also defining the model output directory. So here you see that we're also preparing the logs to be shown in TensorBoard. So this is where we're going to write the logs to. Naming convention here, we just pass the job name so we can find it easily. And then for the Harvard environment, we need to specify here the message passing interface. This is how the instances communicate with each other. So we just pass here a couple of very specific Harvard options in this distribution set. And then we're creating the estimator object here. So it's a TensorFlow model we're constructing. We're, again, giving it the base job name here, pointing it to a source directory. So if you've seen here in the Jupyter environment, we have a directory called code. And in here we have a Python script, which if you open that, it's actually the code we've been executing in the previous 2 notebooks, right? So this is building the model. It has our pre-processing functions in there, save the history, and basically, yeah, the exact code pretty much we've been running before. A couple of things that we changed here is we integrated the settings around epochs, learning rate, etc., as environment variables that get parsed here, right? So this is a way how we can basically give those SageMaker hosted environments and the training jobs here the input variables we specify. So through this parser add arguments, again, we're passing in our parameters to this script, which will be executed later in a container, as we just seen a bit. So this is the script. Let me close this here and go back to the notebook. So we're pointing this TensorFlow object here to this code directory, which will be passed to the container we're building here. We're also saying as an entry point that exact script I just showed you. This is a Python script with a training code. We're passing the SageMaker role we queried, define the framework, TensorFlow framework version, Python version, pass our hyperparameters we defined above, define the number of instances we set and the type, the output path. So this is pretty much what we defined above. We can also give it a couple of tags, so we can easily like search for those later on. So for example, project, Cypher 10, and whatever we want to do. We're also looking for a couple of metrics here. So we're scraping the output to later get the accuracy out of the logs. So this is defining the estimator. So let me run this as well. And then we're defining here where to find the data. So this is pointing again to our S3 bucket. And we're calling the fit command to train the job. So what you see here in this fit command, we passed await false. So this means like we can go ahead and actually run a couple of commands here. If you want to see the output directly here in the cell, you would have the wait true. But in case you want to do some next steps while this is training, this is how you can not have this cell here waiting to finish execution. And then you can also use the attach command here to reattach to that training job and basically see the outcome. So if I reattach here, I see what's happening. So in this case, it's launching the requested ML instances.
Okay, quick note, a couple people are hitting resource limit exceeded, and it looks like potentially my guess, without actually being in front of you, is that you possibly ran that fit command twice, and that both times is trying to allocate 2 of the GPU instances. We only have 2 GPU instances per user, per account. You can go to SageMaker console and look at the training jobs that are currently running. Yeah, actually, can you do that?
Yeah, I can show that. So
I'm just going to show it.
yeah, let me go here back. So in the SageMaker console, if you scroll down to training jobs on the left side, you see the jobs that are running. So I have the one job I just started. You can click in there, and it shows you all of the information. So in this case, we define the P3 to X large with 2 instances. So if you see here a second entry, that means you probably executed that cell twice and started a new training job here, which tries to allocate another 2 GPU instances. So make sure you just have one job running that is in progress.
Okay, so Rada only has one. Yeah, you have one, which means, and the second time that you're trying to do it, it's trying. So actually, if you hit it, if you try to run a second one, it will complain because both GPUs are being taken up by this one training job. So you would have to wait for this one to complete.
So just make sure you see one training job showing up, and you can click on there and make sure it's in progress. You can see, click on View History, and you see here, preparing the instances for training, downloading input data. So this will take a little bit of time to spin up the instances. So what's happening basically in the background here, let me try to show you this picture here a little bit bigger. So what this notebook is currently doing here, we're working from our local laptop or this Jupyter notebook, which pretty much simulates our local laptop. We're using the SageMaker Python SDK within that notebook. We have a training script in this code directory, and we're pulling a deep learning container from the container registry, passing it our training script, which is automatically built through calling this the estimator object through TensorFlow. And we're telling the estimator, well, execute this on 2 P3 instances. So automatically in the background, SageMaker spins up those 2 P3 instances we instructed it to do and deploys those containers to run the training script. And it will get the training data here from the S3 buckets that we pointed it to.
Yes, just to be clear, if you are falling behind a bit, you will not see the job running that Ansha was just showing. I'm getting questions, why don't I see the job? You have to completely run through the CFAR 10 SageMaker distributed notebook before you'll see the job. We were just addressing the people that have jumped ahead or that are actually keeping up, that have seen the resource limit exception, which is they're trying to run a second job.
Correct. So if you're in this Cypher 10 notebook here, the SageMaker distributed, and you're executing here the fit command, this will spin up this training job here in the background. So you can see here the logs in the next cell. This will take a while. So as I said, you can go to the console here and check in the left menu on SageMaker, go to training and training jobs, and this will show here the training job being launched. Updates required.
Yes, we're still here. We're discussing if we should take a break now. There's been some errors here that I want to address, and I want to let people get caught up.
Yeah, let's maybe do a quick break. Grab a coffee.
Yeah, let's do 10 minutes. Come back at 9:45 a.m. PT. I will answer as many Qs as possible during that time. Cool. We'll see you guys in 10 minutes. All right, we're back.
All right, so my script here finished the training job, so let me double check that. So let me maximize here the screen. So I'm back in the AWS console here in SageMaker land, in training jobs. And I see here, can do a refresh, I can see here that my training job is in status completed. So this took 6 minutes, so it's not too bad. Again, if you click here, you see a little bit more of information. Also, what's pretty nice to see here, you see the training time in seconds and the billable time. So by using the SageMaker environment, we just instructed it to spin up 2 GPU-based instances, the 2 P3 instances, and pass the training script. SageMaker pulled down a TensorFlow container, copied the training script into that, and all of the required code, had pointers to the S3 bucket where the data is, and then started the 2 instances and did the training. And the nice thing here is that it's spinning up the instances for us, right? So we don't have to do any infrastructure management here. We don't have to take care to start the instances manually or to shut it down. So the training job ran for 211 seconds, and as soon as it's finished, it also shuts down the instances again, right? So we don't have any idle GPU instances running right now. And you can check it here. So billable time was the 211 seconds from the training job. So pretty neat.
Also note the percentage, if you can scroll back up, Ansha, the percentage spot training savings. So this is important, and I believe this was launched at like reInvent just a couple months ago, but you can now train with SageMaker and tell it to use spot instances to get, I think it's up to like 70 or 75% savings. And because we're using distributed training and frameworks that are capable of handling failures, you can use spot instances, and if they die during the training job, they'll get like replaced with on-demand, so a higher price, but your job won't fail. So this does require that you are using something like TensorFlow that can recover, or PyTorch that can recover from failures. So that's literally one flag you would pass in to the SageMaker job to say use spot instances when possible.
All right, great. So the job completed, and let's jump back here to our notebook. And I push that here to the right again. Go back here to our instructions on the left. So we run that. Basically what we did, and this is just a little bit of recap here in the instructions as well. We had to do a little bit of customization, if you remember here, and I showed you in the Python code where we passed in some of the environment variables. So what SageMaker does is, as shown earlier, describing a couple of environment variables and that we pass to the container. So the training script has to understand those. And if I go back here to our code and open this Python file again, just to show you again, this is the only change we basically did to our training script to leverage the SageMaker environment. As you can see here, we're passing a lot of like those environment variables in here. So this is basically what it's outlined here on the left as well. So the script has to understand those parameters being passed in.
Yeah, this is the trade-off of having a flexible framework like SageMaker. So if they didn't do this, you would have no way to actually pass in these parameters from the outside world. You would be fixed into whatever SageMaker wants you to do. So there's always trade-offs with like flexibility. So super flexible framework like this gives you hooks to like customize. And typically what you're doing here is mapping these directories out to either S3 or to EFS or some file system. You're like basically poking holes into the Docker container and then giving the same environment variables for all the containers to use. So these are just well known. They will always get passed in if you're using SageMaker. If you're not using SageMaker, you would just set these anyway, or you would check here if they're set and then use them. If they're not set, don't use them. Yeah.
All right, great. So let me close down the Python script here again. So those changes we did. So what we can actually also do is, what we've done in the code here is logging to TensorFlow for real-time monitoring. So let's actually do this. So I think it's here. Yeah, this is the notebook we executed. So if you click here on the instructions on the left to the monitoring training progress from the terminal, so we need a terminal session here again. I have mine still open on the Jupyter notebook, and we copy in here this little code snippet. And this starts the TensorFlow service on this local SageMaker instance. And it's reading the training logs that we passed earlier, if you remember, to that S3 bucket /TensorFlow logs directory. So here's the link again in the instructions, navigate to. So I'll copy that one here and open a new browser window. And boom, we're at the TensorFlow environment. So we can see here it reads the logs that are in that S3 directory that we wrote through the training job, and we logged into that directory. And you have a TensorFlow environment now running on this instance, and you can here, play around. You see here the training job listed that we just ran, and all of the information coming here from the log. So we have the epoch log loss here, the accuracy going up. So pretty neat. Make sure here, if you go to that link, to have this trailing dash at the end. This is important. And you should hopefully all see that input here coming up.
Yeah, so I should mention too, so that link appears to be unique or not unique. So workshops.notebook, yep. Amazon does a trick. When you go to this link, it figures out which accounts you're currently logged into and will forward you, right, like proxy you to the correct server, right, like to the correct dashboard. There's like two things going on. They're doing DNS. So my workshop.notebook.us2 is, I can use that in my browser because I'm logged in to the console. This like totally confused me because I thought that had to be globally unique. But yeah, Amazon is doing DNS tricks, which are, like good tricks. And also they let you poke holes with this /proxy/6006. So we launched that tensor board within the notebook instance on port 6006, right there. And yeah, by the way, 6006 is Goog, like upside down, right? So yeah, that was a little joke from Google when they launched TensorBoard. So this actually opens the door to do any kind of web server. You could have MLflow running in here within your notebook. That's going to be part of a future like workshop. We're not doing MLflow today, but you could have that port listening and then proxy through this way.
All right. So hopefully everyone got to do the distributed training with GPU instances, and you really saw how easy it is to kind of scale out here, right? So again, we passed the instance type, we selected a GPU type here, increased the hyperparameters like epochs to 5, etc., and said spin it up on 2 instances, and boom. So this is the power of having managed infrastructure through a cloud and being really able to quickly scale out and leverage the power of the cloud here. All right, so this completes already this second part. And the third section is really a little bit longer, where we take time to spin up the Kubernetes environment. And we're going to use Amazon EKS for that purpose, so the managed Kubernetes environment. And we're going to spin up Kubeflow. And then we're running through a lot more examples and notebooks inside of the Kubeflow environment then. So for the first part here, again, what we did a single node training. We prepared the training script to be distributed. And then we used SageMaker to run that script in containers and scaling out through more instances and doing distributed here. So with part 3, as I said, we're now doing distributed training with Kubernetes and Kubeflow. And this part will be presented by Chris, so I'll hand over here to Chris.
Okay, yeah, just 1 second here. Yes, I actually have to reboot my laptop for a security patch to install.
So this happens if you ignore the warnings for too long. Okay, so I'll start with that part until that is figured out. No worries. Okay, so let's start with part 3. So if you follow here in the left in the instructions, you can close down the notebooks you have open here. I'm gonna Control C out of my TensorFlow environment here. We don't need that here. Gonna clear the terminal. If you go back in the Jupyter environment and you go to pod 3 Kubernetes, this is where we're gonna start right now. So what you see here is actually a bunch of folders and notebooks, so don't get scared. We'll walk you through this step by step. But basically, the most important for now is the Docker folder. So once we create the Docker images later, you can find here in the code directory again our Python code. So this is again the training code. We're actually reusing the same training script here through most of the content. So again, this is the training script we're now all familiar with. Not too many changes here. And what we added here is basically a Docker file. So Docker files are used basically to build custom container images. And you can click into here, and for those of you who have been building Docker images already in Docker containers, this should be pretty straightforward as well. We're basically pointing out here a base image we're using. In this case, it's really just a Python Ubuntu image. Again, we're copying the code we have into a folder accessible in the container. So this is going to end up in opt training, and this is also going to be our working directory in the container.
Yeah, we should point out too that this is not SageMaker anymore. So the reason that we're seeing opt training instead of opt ML model, like I mentioned previously, is because Kubeflow does not follow the SageMaker standard, and nor should it follow the SageMaker standard. I actually recommend to Amazon customers that they do follow the SageMaker standard. You could choose any standard for naming these things, but if you do use opt-ML model, then you could swap this in to SageMaker very easily. So here we're just making an arbitrary choice to copy it into opt training, and then our code has to use opt training within. But yeah, that's why things look different.
All right. So this is the CPU version, and there's also a Docker file for the GPU. So this is just basically pulling in another base container image here, GPU-based Python Ubuntu image. So we're going to reuse those later on. So if you're in the part 3 Kubernetes, let's move on. So another folder maybe worth looking into is the specs. And if you have been working with Kubernetes before, basically Kubernetes gives us a declarative way to describe our resources. So those are the famous YAML files. And here in the specs folder, you see a couple of those YAML files we use throughout the rest of the workshop here in this Kubernetes section. We're gonna, for example, here define a TensorFlow training job, one for the CPU, one for the GPU version. And you can sneak peek here if you want to into those YAML files. And this is basically how you tell Kubernetes what to deploy. So you're defining resources, you're defining training jobs. So this one here is, for example, an MPI job. We call it the EKS TensorFlow distributed training. When we later deploy that, it's going to have 2 replicas. So it's going to spin up 2 environments here, 2 versions of this MPI job, and it has all the commands needed to execute. And what we're also doing here is basically we're introducing here a distributed file system as well. So one thing you want to make sure if you're working in Kubernetes and you have a distributed training environment is that you probably want to have a distributed file system. So where like all of your containers. So where we just were here in the Kubernetes land, I just opened up one of those YAML definitions here for the training job. So and here in the volume mounts, what I just said is like you probably want to have like a distributed file system as well to have like all of the pods giving the access to, for example, this training data that's stored. And we're going to actually set up a distributed file system here in just a bit. We're going to use FSX for Lustre, which is basically a way, a file system Amazon provides to have very high performant access. So this is used especially like in machine learning, deep learning environments or HPC environments. So really giving us a pretty performant way to get access to the data. All right, so those are the YAML files here. So I click out of here. So those are all stored in the specs file folder here. So let's maybe just give you a quick overview here of what's happening in this chapter. So we're going to set up our Kubernetes cluster here in just a bit. We're still operating here from our Jupyter environment, and basically what's going to happen is, again, we're going to create a custom container with our code and have that in the container registry. And then we're going to use that to deploy on the Kubernetes cluster later to do the distributed training. So this is just like in comparison to what we've done before. Instead of using SageMaker as the platform to deploy our distributed training job on instances, we're going to now do distributed training on Kubernetes, right? So it's going to deploy our pods. So pod is basically the concept of Kubernetes, like one or more containers forming a pod. It's a logical group, and the pods get deployed on the cluster. And we're using this Amazon FSX for Lustre file system, which basically provides a high-performant access to the underneath data that is in S3. So this is kind of a high-level overview what we're going to set up here in a little bit. So let's click here to a couple of preparation steps we need to do. So again, we're going to execute this from our terminal environment. So you hopefully have still the terminal window up, otherwise just open it again with a new terminal. And what we're doing here, just in case you had the terminal window closed, we're doing a quick source of the bash profile to have our environment variables like the S3 bucket name, etc., accessible. We're jumping into the SageMaker Kubeflow part 3 Kubernetes folder, so the ones where we're executing in. And then we're doing a couple of installs here. So the first one is we're installing, pip installing the AWS CLI, and we're pulling in also a couple of tools. So for the managed Kubernetes environment, the EKS, Elastic Kubernetes Service on Amazon, there is actually an additional kubectl, which is called the EKS ctl command or EKS CTL command, which helps us to easily spin up an EKS cluster. So this is very specific CLI tool to do basic operations with EKS, pretty neat. So we're going to pull in that one, install that. We're obviously also installing the kubectl environment, so we're pulling that one in. Change mode here to execute. And what we also need to do is, again, everything in AWS needs to have dedicated permissions to be allowed to execute things. So we're also pulling in an AWS IAM authenticator, which basically allows later on the EKS resources to actually perform things, right? So this is taking care of the authentication of the environment. So it's really a couple of pre-installs we have to do here. So we can do them in bulk. So again, in the top right here, you can just copy that whole code snippet here, copy to clipboard, and then paste it here in your terminal window. So as you can see, it's pulling down a couple of pip installs here, installing the tools. And again, check for any errors. This one worked fine here, as you can see. So it installed. It also copies in the comments here, but they should not create any harm. So did the curl, did the settings. And the last command here is actually double checking that everything is also in the path. So you see here in the last couple of lines, the kubectl, JQ, and the environment subs is all in path. So everything is set. So we're able to call it. And we saw the completed. So just make sure this runs without any errors. And then we can move ahead and also get started with setting up the Amazon EKS cluster. So in the next step here, I just clicked one step forward here in the instructions. So in the next step, we need to set a couple of parameters needed. So we're going to set the AWS region. So this is US West 2 we're operating in, and we're also setting our cluster name. So again, just copy here, click the clipboard icon here, and let me do a quick clear here. Copy that one in. And this is pretty fast. It's just setting some environment variables. And in the next step here, we're basically starting the creation of the EKS cluster. So copy that command and also execute this in the terminal. And this will now actually take roughly, I guess, around 15 minutes. So it's creating our EKS cluster. So it's spinning up a lot of resources needed. You can see here it passes the cluster name, sets the version, the region we just defined, and basically uses a C5 X large as the node type for our EKS cluster. It will set up 5 nodes. We have the volume size defined, etc. So this will take a little bit of time to set up here.
It's probably a good time for a break. Let's consider this, I guess, the lunch break. This does take about 15 to 20 minutes. So let's come back. Let's come back at, let's see, 10, 15, 10. Let's come back at like 10:40. 10:40. Yeah, we're making good time, actually.
And we're making sure everyone is at this step.
Caught up, yeah.
Yep.
Because, yeah, everything after this depends on that cluster starting. So please ask questions. We're going to go on mute for a bit. We'll put the time in here in a sec. Come back at 10:45. Yeah, let's come back at 10:45. Take a half hour.
All right, so it's 10:45. Let's see. So my cluster deployed. So you should see, and I think a couple of you already went ahead with a couple of instructions here. So hopefully everyone can see this echo completed here in the screen, in the terminal window. So, and the last line here printed in this blue-green color, EKS cluster in US West 2 region is ready. Where you can also check, we've been just answering in the chat window here a couple of questions, but I want to show you. If you go to the AWS console and you look for EKS, that is the EKS environment, and you see the cluster name here. It gets provisioned as Pipeline AI as the name, and you see the status of active here. So this one turns active a little bit earlier than the terminal will say complete, because it's finishing up a couple of more tasks in the background. But you should hopefully see the status green and active, so you know the cluster is in a healthy state here. Okay, so let's see. Another thing we just discovered, a couple of you that went ahead with setting up the environment probably missed the step that was just mentioned below here. So Chris just split that to the next page just to make sure nobody is missing that, because it's setting up some important variables, and then you might be running into issues later if you set up the FSX for Lustre, because some parameters and variables are not set correctly. So we just split that. So make sure you do a refresh on the instructions. Just reload that site so you pick up the changes that Chris just pushed out here. Okay, so if everybody can see this completed here, click on the next screen here in the instructions. And this is the section that a couple of you probably missed because it was underneath in the previous screen before. So this is again making sure in case somebody closed the terminal to source the bash profile again. And then we need to set a couple of parameters here. So we're doing some export and running some EKS cattle commands here. So we're setting the stack name, for example, and we're setting the instance role name. I think that one errored out for a couple of you as being empty later on. So make sure that you run this step here, which actually sets the variable. We're also setting instance profile RN. And then we're also attaching, again, a policy here, the Amazon EC2 Container Registry full access, so that our EKS environment is able to access the EC2 Container Registry. And basically, yeah, set up the cluster identity. So let's copy this command here, again, in bulk. Let's do a quick clear on my terminal. And let's issue that. Make sure everything, again, succeeds. The last one is here. You do the echo completed. So you have to hit enter here, actually. Doesn't pick up the last line. Do your own echo completed. So checking if everything executed correctly. So this looks fine. So it actually created the IAM roles, policies, and connections here. Okay, so let's also update our kube config file. So this is the next section here. Again, I'm just pasting that in here. And this basically is writing out all of the configuration parameters and creates this in the .kube folder, the config file, which contains the information about our EKS cluster. So with that, we should be able actually to check. So we can run the kubectl command here, kubectl get namespaces. And you should see an output here, like, for example, default kube node lease, kube public, kube system. Those are the namespaces, the default namespaces that are being set up in the cluster. And if that command doesn't run correctly, you probably missed one of the steps before. So this way you can check. You can also run the kubectl get nodes command here. And here you get the 5 instances we told EKS to deploy. So those are the 5 nodes, the 5 instances that form our Kubernetes cluster. So make sure you're seeing that output here and make sure everything is configured correctly. So as I said, Chris just split that into a second page here. One of that step was like mentioned here underneath the deployment. So make sure you do a quick refresh here on the instructions to pick that up. Run the finish and verify cluster installation. And once you're seeing the namespaces here with the kubectl get ns and the kubectl get nodes, you should be in a good state. All right, so in the next step, we're going to introduce the distributed file system. So we're going to enable the Amazon FSx for Lustre access. And as I previously said, this is basically a high-performance file system, really optimized for either HPC environments or also used pretty much in deep learning, machine learning environments. And what it does, it basically sits on top of S3 and presents the S3 objects as files. And this allows you really to quickly write results also back to S3. So this is super helpful in our case here for the Kubernetes environment. So what we're going to do is also, again, like run a couple of commands here to actually pull down the Kubernetes manifest. Again, set a couple of parameters, so VPC ID, the subnet ID, security groups. So it's a lot of configurations that go in here. Just again, copy the whole bunch of commands here and execute in your terminal. In the specs?
Yeah, so there's a specs directory I'm just going to pull up, fsx-s3-sc. If you crack that open, this has been processed, and we ran a sed script as part of the magic script here that slammed in your S3 bucket into the configuration of the FSX file system. So this is backed by S3. It's the exact same bucket that we used to copy the data set in part 1. But now there's a layer on top called FSX for Lustre that gives you POSIX-style file system semantics. And it'll take care of the reading and the writing to S3 and the caching.
Yes, so you can see the file here in that specs folder, which I pulled up earlier. So have a look at that if you're interested how you actually write those. All right. So let's see, terminal completed. So you can also check again, the FSX will take a little bit to provision. So again, you could jump back to the AWS console here. And in this case, look for FSX. Go down there. And you see here, it's being created. So this will probably take, we can go ahead with the content, but in the background, this will work for probably another 10 minutes to be provisioned. So you can check here whenever it is ready. But we can actually go ahead with our workshop content. So let's see. So we started the provisioning of the FSX file system here. And in the meantime, while this is getting ready, we're getting started with Kubeflow here. So in the next step, we will install Kubeflow. And again, we kind of brought all of the commands you need to run here together. If you're like interested in how you like step-by-step set it up, you can have a look here at the different components and the different steps. So we're making sure all of the variables are set. We're downloading the KS control, so the Kubeflow control CLI tool here, giving it permissions, exporting configuration, setting specific Kubeflow environment variables that are needed, KS name, for example, making sure we're in the right directory, also pointing then the variable Kubeflow directory to this, and yeah, doing a couple of more settings, again, replacing some information here with the instance role name, for example, our cluster name with the set commands, and then we're calling the Kubeflow control build and apply commands here. So it's a pretty extensive set of commands to run. So I'll, again, copy those here and clear my terminal and execute those commands here now. And you see here in the background a couple of, actually a ton of resources being deployed on our Kubeflow cluster that are specific, on our Kubernetes cluster that are specific to Kubeflow. So the last one here is just a comment. So we'll have to wait now a little bit until this is provisioned. And then we'll go to the Kubeflow dashboard as soon as this is running. So I'll grab here the following command. Yeah, my browser jumps here. There's a little bit of a UI bug here. Boom. So I'll issue the next command here. And here I get a link. So copy that host name here you get returned from that command. So it's the number hash istio some numbers US West 2 ELB Amazon AWS.com. And you can paste that in a separate browser window. And it takes a little bit of time to start. So just be a little bit patient and rerun that until the Kubeflow dashboard actually shows up. So we know that Kubeflow is provisioned. I'll just do a couple of refreshes here once in a while. So as you can see here, and we had a couple of questions earlier, like how does SageMaker cluster compare to Kubernetes, EKS, and Kubeflow? So I mean, you already see like that there's a lot of work involved actually to set up the infrastructure, right? To deploy a cluster, to set up and deploy Kubeflow. And with having a managed service like SageMaker, we didn't have to think about the underlying infrastructure too much, right? We just defined like how many instances we need and what type, but we didn't have to basically run a whole lot of like infrastructure installation. And this is really here in contrast. So the Kubernetes and Kubeflow route is really if you have like dedicated teams that are familiar and can help in setting up Kubernetes environments and also like operate and maintain them. You can obviously use the managed services like EKS. But as you see here, it's still a little bit, of configuration and setup in the process. So the dashboard here came up. What you can also do is in the terminal to run a kubectl get pods command. And this shows like all of the pods. And you might see some like creating state. That means it's not yet finished. If you see like all of the pods here are running, that means like it's finished in deploying everything. So again, you can run the kubectl get pods, and this shows you all of the running pods here with the status, whether some are in creating or if all is in running state already. All right. So once you refresh here that link that you received with that command here from the instructions, this is the start screen here from Kubeflow. So we have Kubeflow now installed and running on our EKS cluster. So we're going to set up here the Kubeflow environment, and then we're getting into another round of notebooks here and show you what you can do. So we're going to click here on Start Setup. In the namespace, again, I follow the instructions that I show here on the left. So I'm going to call The UI always jumps. I'm going to call here my namespace EKS workshop and click on finish. And here we go. So we have a brand new fresh install of Kubeflow. So make sure everyone to see that dashboard before you go on now with the setup here. So this means that you successfully installed Kubeflow, and then we're setting a couple of more credentials that we need to have access. So I'm gonna jump back here to my terminal window, and here we're setting some additional parameters. So we're creating an S3 user and attaching policies again, and again writing out some variables we need here. The AWS access key ID value, secret values, and we're basically creating Kubernetes secrets so that the Kubernetes cluster can then interact with instances and the services we'll need. So just again copy this whole collection here of commands into the terminal window.
For those of you that accidentally clicked through and didn't use the the EKS workshop namespace, you will be okay. I actually put a note in there. This happens all the time. People just click through. You'll be okay. There's one spot, and we call it out to say where to use that namespace name.
All right, so it's a lot of commands here. If you get the echo completed, make sure, again, it all executed without any errors here. So this looks good. It copies all the comments in here, but that doesn't bother too much. Just make sure everything executed and you get the completed. All right. We're almost there. So in the next step, what we're doing, we need to create a container registry repository. So we will be using Docker images, creating Docker images, pushing them. So we need a container registry to use. So in this step, we're basically creating an ECR, which is the AWS Elastic Container Registry repository. And again, we need to set it up with the correct credentials, and then we can actually already run a Docker build command. So let's issue that command here. Let's do a quick clear here on the screen. So what it does, it creates a repo named workshop, and then it saves again the values to environment variables. It logs in to the AWS Deep Learning registry. So we need this login actually to pull our deep learning-based containers that we're using. So we're logging in here, and then we're changing again to our Kubernetes Docker folder, or the folder here we have that contains our code and the Docker files. And with that Docker file, which I showed earlier, so let me go back here. So it's part 3, it's the Docker folder we're pointing it to, and we're using here the Docker file CPU. So we're using that Docker file to create a container. So it's pulling down here the needed information, and then it executes the Docker build, and then we're logging into our registry and pushing the Docker build. So this is currently happening here. You see the data is being transferred. So this takes a little bit. So again, quick recap. In this steps, we logged in the AWS Deep Learning Container Registry to pull an existing deep learning container. And now we're building it containing our code, and then pushing it again to our repo that we just created in the first step here. So the push completed. So what we can now do is we're actually pushing or creating a distributed training job here. So we're making sure we're in the right directory, replacing, again, a couple of parameters here, like the Docker image and the repo we just created in the YAML file. So we're using, if I go back here again, I think it's in the code, no, it's in the specs here. We're using the EKS TensorFlow training job CPU YAML, which I showed initially. So we're using this YAML to create an EKS distributed training job. So this is what you can see here on the left, right? And we're just passing our variables. So you see here your Docker image, etc. So we're replacing that here with those set commands you see on the left with the current values. And then we're passing that YAML file to the Kubernetes cluster via the kubectl commands. So you can see here on the left the kubectl create default, and then we're passing that file. So this is the command we're running, and then we can see basically the pods being created and the training job being executed on the EKS cluster. So let's do this. So we push the container here, I clear the terminal, and then again I grab that command. I execute it here in the terminal. And boom, you see here, it's also including a kubectl get pods command, and we're grabbing for exactly that EKS-TF-distributed training name. And you see here the container creating. So if I rerun that last command here, just go up a little bit, you see here the two workers. So we defined in that YAML file if I go back in here, we defined two replicas. So this is the two workers you see being deployed right now. And it's in the container creating state.
Okay, I think we should pause for a little bit. And if anyone's having problems, could you please let us know? I'm seeing a couple people having some problems. Maybe just for about 30 seconds here, pause. All right, yeah, Richard, we'll have to take this offline. I'll have to work with you directly on this. If everyone else is caught up, let's keep moving ahead. Yeah, Richard, go back and just rerun install Kubeflow and just keep trying that. Okay.
All right, so I just rerun this kubectl get pods and grep for this distributed training job, and you can see it's in state running right now. Right, so currently we have those two workers executing our training job. So we're doing literally distributed training here on Kubernetes. So what we can also do here, if you look in the next command, sorry for the jumping UI here, I'm actually going to see the logs. So I'm going to copy that part here, and I need to pass the exact name here. So let me copy that name. So do the kubectl logs -n default, and then pass the name of the launcher container running here. And this basically shows you the logs from that pod. And you can see here familiar content, so it's actually executing here the training job of our famous training script we've been using all day. And you see here it's currently in epoch 2 from 10. So yeah, congratulations, high five. So we just did a distributed TensorFlow model using Harvard on Kubernetes on Amazon EKS using the FSX for Lustre distributed file system backed by S3. So it looks pretty like, you know, like just typing in a couple of commands here, but we actually just set up everything. So we set up the EKS cluster, we installed Kubeflow, we set up the container registry, and we created our own container, and we pushed it to be deployed with Kubernetes and running our distributed training job in this environment.
Yeah, can you show the very last command? Can you just press up arrow?
Yeah, sure. Let me clear that screen here. So it's in here. If you're in the submit distributed training job in the instructions, it's the kubectl logs command. So the only thing you have to do, if you run the command before, where you actually the do get pods and you grab for this name, the EKS -tf distributed training, it returns the list of the 2 worker nodes and the MPI job, the distributed training launcher job. So you want to grab that because it has like a specific, like a hash, right? So I'm like, in my case, it's this B8 WSS. It's going to be a different name in your environment. So what you need to do is run that lock command that's stated here next, and change the last bits here to your specific pod name, which will have some letters, characters, and then numbers in here.
Okay, someone asked if Kubeflow handles errors, for example, restarting workers if one fails. That's actually a feature of the EKS. As EKS will restart it. And if you're using a framework like TensorFlow distributed or PyTorch distributed or Horvath, it can recover those frameworks can recover from failed nodes, but that's more of an EKS feature.
All right, so you can keep looking, sneak into that. I'll quickly have a look here. Yeah, my file system is actually, so in case you see any errors, make sure the file system has been deployed correctly, because we're actually using it here. So I should have checked that before. Luckily, mine was deployed, but if you're seeing any errors here, make sure your FSX for Lustre has successfully transitioned into the available state. If that is still deploying, you might not be able to run this training container pods here. So mine is doing training. It will take a little bit longer here. Epoch, where is it? 4, 5 from 10 now. Okay, so we can actually move ahead here. So we've pretty much like interacted with Kubernetes now through the terminal window here. What we're doing next is actually we're switching to the Kubeflow environment and then run the next notebooks through the Kubeflow provided notebook instance. So this is a little bit confusing here. So just watch out. So until now, we've been using the Jupyter instance that has been hosted on SageMaker, right? So we went in SageMaker in the beginning and created this notebook instance. We cloned the repo and run the code and the notebooks. So what we're doing now is we're jumping into Kubeflow, and Kubeflow also has hosted Jupyter notebooks. So this is a little bit confusing. So if you're actually done with those SageMaker notebooks, you might want to just put that browser tab away or even close that, not to be confused too much. Just bear in mind that we're jumping now to the Kubeflow world. So I'm closing down, for example, my terminal window here, and I'm going now to the Kubeflow dashboard that we had before. So again, if you haven't that one open yet, go back to the Kubeflow setup, where we had the command to show you that the exact address where you can find it. So once you're in the Kubeflow dashboard here, select the namespace you created. So in this case, EKS workshop, to make sure we're in the right environment here. And then we're basically creating another Jupyter Notebook server through the Kubeflow environment. So in the top left here, you have a little hamburger menu. You can click here and you see Notebook Servers. Click on that, and you see there's no server running yet. So what we're going to do is we spin up a new server through Kubeflow. So click on New Server here, and we're going to get it the name. So you can copy the values here from the instructions. So we're going to call it My Jupyter. Make sure it's in the namespace EKS workshop. And we're giving it a custom Docker image to start with. So make sure you're copying the image name that's provided here in the instructions. So it's pipeline.ai/kubeflow/notebook CPU as a custom image. And also make sure to increase the CPU, not to 10, the CPU to 1.0. So bump it up a little bit on the CPU, and that's it. So Kubeflow dashboard, change to our workspace or our namespace, EKS workshop. Click on the top left for notebook instances and create an instance, call it my Jupyter. Make sure it's in the namespace. Provide a custom image. You find the custom image here in the instructions on the left. Increase CPU to 1.0. And keep the rest as defaults. And then you can hit launch. So this is now spinning up a complete new notebook server in Kubeflow land. And once this is up, we can connect, and then we're again cloning our repo and run some of the more advanced notebooks here to show you more exciting things. So this might take another minute here. It's not taking too long, but I guess between 30 seconds and a minute here to come up.
A couple people are still back on trying to do the kube the kubectl logs for the launcher. So check out the chat. I just put the command in to run. You don't need to do that, by the way. You could just keep moving ahead, but if you do want to see it.
All right, so my Jupyter instance came up. So you see the little check mark here, status available, and then you can click on the connect here. And surprise, we get another Jupyter instance. So this is the point where make sure you're not getting confused in which Jupyter you're in. If you're running one of the later notebooks from the SageMaker one, it might error out here and then. So you can double check. So if you're looking here in the address, it's something like this number code Istio system. Istio, that's the Kubeflow notebook. And if you see the workshop notebook, that's the SageMaker world. So make sure you're in the Kubeflow Jupyter instance if you happen to have a couple of windows and tabs open here, not to get confused. Okay, so in the Kubeflow environment, we're just going to use Kubeflow for the rest of the workshop. Let's do new and open up a terminal window again. And we're going to git clone again our repo. So issue the git clone command here. And with that, we're back here in our Jupyter environment and have our Kubeflow repo here. I just closed the terminal here not to get confused myself. And if we go to notebooks and part 3 Kubernetes, we have a bunch of notebooks here that we're going to run now from this Kubeflow environment. So just going to make sure that people are following here. So give me a second. All right, so I think Chris is taking care of most of the questions here. All right, so if you manage to git clone the repo here and you see the notebooks, we can go ahead and actually I can minimize my instructions here. So basically the instructions is set like run the notebooks now. So let me maximize here my environment. so that nobody gets confused here. All right, so let's start with the 0, 0 here. So let's open the 0, 0, which is just really a first exploring notebook. So let's just run through those cells here. Boom. So what you see here, and again, ignore the warnings. It's printed in red. It's a little bit scary. I always get scared, but it's future warnings. So we're basically importing TensorFlow here. We're printing the current TensorFlow version. So in this example, we're still using 1.13.1. And we're checking here the Python environment. It's 3.68 from Anaconda. We're doing a pip list, so to check what is installed. So this is really like just exploratory, right? So whenever you want to execute something from the notebook here directly in the CLI, you can do with the exclamation mark. So we can do the pip list here from the notebook. What we can also do is like with a %% bash, basically jump directly to let it know it's bash commands, so we don't need to have the exclamation mark. And for example, here we do a conda list. And also what's exciting, not sure if everyone knows that, you can also render HTML inside the notebook. So if you do a %% HTML, you can then maybe show an iframe, for example. So we're just pointing this iframe here to our book website and can actually display that as part of a notebook as well. So pretty fun. So this is just, exploratory. So let's go ahead, open the next one. So 0001. Let's run through those cells. So again here, we pip install NumPy. We're also like pulling back our famous training script here with the settings, downloading the data, training the model here. So this is basically what we've done before. We're now just executing everything from within Kubeflow, right? But this is still like doing it locally here on my notebook. So different ways to do things, really. You have, as you can see, there's a couple of options how you do certain things. Also, there's a quick note if you want to read through this about sharing your notebooks. So obviously, a good practice is if you don't want to share like the outputs, you can click on cell all output clear. To make sure you're not sharing like your executed code outputs here with anyone. And you can also, if you want to save some files and notebooks, you can do always a file and download as. I think the more advanced Jupyter users should be pretty familiar, but maybe some of you might not know. So yeah, that's pretty straightforward. First couple of notebooks. Let's move ahead with those. The next one actually is a little bit more interesting. So that one is also exploring from Kubeflow, from this notebook here, the underlying Kubernetes cluster. So if we do, for example, again, an exclamation mark for running a CLI command and do the kubectl get pod command again, we see here the my Jupyter pod is running. And if we describe that pod, we get more information here. So like all the settings, containers running, images used. And then we can also again look into the logs here and see what's happening here in this Jupyter pod. So this is basically the pod that is hosting our Jupyter instance right now. All right, let me close those notebooks here. And yeah, Chris, you want to take over for your favorite topic, the fairing?
Yeah, I can take over for fairing. Let's take about a 5-minute break. Come back at 11:30. Let's come back at 11:30 a.m. PT. I'm gonna finish answering questions here, getting people further along. Okay, see you in about 5 minutes. All right, coming back, I think I cleared most, hopefully all of the questions. Yeah, a lot of good questions here. Someone just asked about SageMaker Studio versus SageMaker. Let's get to that later. After, I want to focus on Kubeflow. The short of it is SageMaker Studio is the next evolution of the SageMaker Jupyter notebooks. Has a nice UI to view experiments and lots of other cool little features. It's based on Jupyter Lab, if you're familiar with Jupyter Lab, which is next generation Jupyter notebook. So Jupyter or SageMaker Studio is not in the region that we're using, US West 2. It's also in preview, and right now is not the most stable, to be honest with you. So let's, but yeah, keep an eye out. I mean, basically, you can sort of unify all of your data science into one UI. Our book will be covering Studio. Someone asked why they couldn't allocate a 16 gig Jupyter notebook. The reason for that is the C5X large instance type that we're using. I'm going to send you guys a really fancy link here that I use on a daily basis. ec2instances.info, created by a friend of mine a bunch of years ago. I use it all the time. I actually have it integrated in some applications, things like that. C5X large, that only has 8 gigs. Each node only has 8 gigs, so there's no way to find a node in the cluster that can hold 16 gigs. This was a choice we made just to keep the resource utilization low, so that we're not occupying, spending too much money. But if you were to do this and insisted on a 16 gig Jupyter notebook, you would have to have at least one node in the cluster that can handle or that has 16 gigs available. Same if you were trying to allocate 16 CPUs for your Jupyter notebook. The thing to keep in mind is your notebook should be thin and your cluster should be big. So you shouldn't be running a Jupyter notebook that requires 16 CPUs or even 16 gigs. You should be offloading that kind of training to a cluster. Okay. Let's see. Okay, so let's get going here. Switch over. Alrighty. So. Okay. There's a project in Kubeflow called Fairing. So Kubeflow it's a bunch of projects kind of, at one point they were loosely coupled. So you have Jupyter notebooks, you have, so you have Kubeflow notebooks, Kubeflow pipelines, this project called Kubeflow Fairing. Fairing is meant to give you the ability to train inside of a notebook, kind of do ad hoc training, and then take that exact same code and run it on a cluster. So all of Kubeflow is Kubernetes native. So yes, every single component that runs within Kubeflow has to be a Docker container, which requires a Docker image. Fairing gives you kind of slick ways to create those Docker images behind the scenes. And that's what we're going to show here. So let's install Kubeflow Fairing 071. Here's a fancy little script. Sometimes when you install dependencies in the Jupyter notebook, they don't get picked up, and there's all kinds of tricks and things you could do, but here's a nice little piece of script that you can run that will actually restart the kernel and pick up. So I always like to put that in there. Pick up the new pip installs. All right, here's a train method, a train function that we're creating within our Jupyter notebook. We've got imports. We're importing TensorFlow. This is pretty primitive, old school TensorFlow. We're just showing you can pretty much do anything. Let's run the training here at the very bottom. We're just invoking train. So this means that we're running this training job directly in our notebook. And I just got done saying that you don't want to do this for large data sets. You want to offload that onto a cluster if possible. All right, so we trained. We got final weight, final bias, cost function, see cost. So not a very good model, but that's not what we're going for right now. We're just showing. Okay, now we're actually going to log into ECR. So ECR is the Elastic Container Registry. This is basically privately hosted Docker Hub, or privately hosted Artifactory, if you will. So we're going to log in because what we're going to do is create these Docker images and push them to our ECR repo, and then point our cluster to that repo. Okay? Don't worry about that error. That's just an initial thing saying it's not there. If you rerun it, you can rerun this multiple times. All it's doing is just creating this one time. That's creating a repo that we're calling fairing job. We can call it anything, but we're just calling it fairing job. So this is just telling ECR to get ready for some Docker images that are going to be pushed. Now we're actually creating the Docker. So this is the ECR Docker registry coordinates. This is saying use a base image of TensorFlow 114. If we were doing 2.0, we would do TensorFlow 2.0 here. And then we're actually giving it the name of the function. So if we called this, if this function up here was called my_train, we would have to change what it's called down here. So this is the actual function. And then we're calling that, and so this is trying to make 1 or 2 lines of code. It looks like, it's 5 or 6 lines of code here that is building the Docker image in the background, and then pushing the Docker. So here it actually built the Docker image, then it pushed the Docker image into the ECR repo. Now that the Docker image is in the ECR repo, our Kubernetes cluster can distribute that Docker image to multiple nodes in our cluster. We have a 5-node cluster, and all that can be accessed. And so this is actually showing a sample run. It's the exact same code that was used in the notebook, but now it's actually running on the cluster. So once again, this is not a very good model. We've only done 1,000 epochs. We're not doing any hyperparameter tuning or anything here. It's just showing how to get this done. So if we wanted to, we could go into ECR, go to Services, Elastic Container Registry ECR. We see fairing job, and we see the Docker image that was just created. We see the size, 482 megabyte. That's partially because of the base image being pretty big, having TensorFlow, but this is physically the name of the image, and that's what the cluster is using. Okay. So where were we here? Part 3. All right, so let's take it one step further. Here, we're actually going to not only build the Docker image using fairing behind the scenes, we're actually going to do this slightly different, where we're going to give it a requirements TXT. So before we were just using TensorFlow. Now we're using XGBoost, Scikit-Learn. We're going to prepare this for model serving by pulling in Tornado, some other libraries. And we're going to pip install the requirements here, right in the notebook, so we know we have the exact same environment in the notebook versus outside the notebook. We're going to run our fancy script to restart the notebook and pick up the pip install. We're going to log into our ECR repo. All of this can be handled without username and password because we're running in Amazon, and these workers have been authorized. So the 5 nodes in the cluster have been authorized to talk to ECR through the backend IAM roles. And we did that actually, that was part of some of those big horrible scripts that we were running. We were giving the worker nodes that authorization to talk to the Docker repo. So now all we have to do is just call login, and then behind the scenes, all the tokens are being passed, and there's no credentials or secret keys being passed here. Describe the repo, fairing job. Okay, it found it, so it doesn't need to create it. And here's a slightly more complicated model where we have Scikit-Learn to do some feature engineering. and imputing, some train test splitting. We're also using XGBoost, XGB regressor. Let's train the model right in the notebook, just to show that there's nothing up our sleeve here. This thing is working. MAE is pretty awful. That's not the point here, though. The point here is to get through this. So we're just giving this a name. And let's see. Just following, this is pretty much boilerplate stuff here. All we have to do is give the account ID, the region, the bucket, and then we're now using something called train job here. So train job is just supposedly like an even slicker way to do this besides the 1 or 2 lines of code that we were doing before. It's just a slightly different way to actually do this. But at the end of the day, we're showing, so like 2 different ways to do this. And here we're actually passing the requirements txt, the exact same one that we used up above when we did the pip install to prepare the notebook environment. All right, so this is starting the pod. So not only does this build the Docker image and it pulls in the requirements txt, but this is also going to deploy it onto the cluster. Here we see the requirements txt. And if you don't specify a base Docker image, it will automatically choose one. It looks like this one chose Python 368. So before we were giving it TensorFlow 114, now it's just using just a base Python 368 that was available from Docker Hub public repo. All right, so this should be and the reason that we included some of the prediction libraries up above, like Tornado, which is web server kind of thing, we're going to attempt to deploy a prediction endpoint. So I don't know if this finished yet. The training hasn't actually finished yet, but once it's finished, it's going to deploy. It's going to set up a cluster IP, which is internal DNS. So this notebook is running on a Kubernetes worker node, and it can get to other worker nodes wherever this model ends up for serving prediction. So these should be able to talk to each other. Ansha and I were having problems last night. Something broke since last month when we did this. This was working last month. So not sure if this is going to work 100%, but this is how it works. You would deploy it, and then eventually it will start up a pod that we can get to. This is going to tell us the endpoint, I believe, when this is done. And then we'll slam in the endpoint there. We'll then get some data ready for testing. And then we would actually run the predict. This should probably be test CSV, but let's give this a moment. Still running. I can't remember how long this took last night. Do you remember how long it took?
Not too long, I think.
Okay. So anyway, I think you guys get the idea. We would get the endpoint from this. We'll print it out at the very end. We would then put that endpoint in here, and then we can make a call. There's this function called predict NP array, so predict with a NumPy array. This saves you from having to convert it to JSON or some other format. You could actually just pass in the NP array, which is very common format for data science. Okay, so let's keep going here. Here's the TFX stuff that is broken because of those data sets being missing. Dean pointed out that the data set is available in BigQuery. I just haven't had a chance today to try to save it out. I have to make sure it ends up as the same format, data CSV, I tried with a different Chicago taxi data set, or the same data set but in a different format last night, it didn't work. This is the link that is broken. This is actually broken on Google's Colab as well. Oops, that's the wrong link. So the short of it is the TFX samples here are broken. Apologize for that. Yep. So they moved the data set, and even their stuff doesn't work now. So not much we can do, but the general idea here is that TFX has something called TFX data validation, which can analyze your raw data set for missing values, for high number of zeros, for sort of abnormalities. And that way, if you do start getting in data that does not match what the similar distributions from like previous drops of data, then you would want to actually stop the pipeline and page the data scientists and figure out what to do. Oftentimes, this is an upstream issue with your application. The application team started writing nulls to a field where that was previously required, or they started writing duplicates, and these are things that you have to halt the pipeline or somehow work around and then work with the application team. You can also generate a schema from the data with this like TFX data validation. And this is pretty cool. The downside here is this is using the Apache Beam project, and it's kind of tricky to debug. It's going between Python, there's C++ code, and then Beam is in Java. So there's like lots of different places for things to go wrong here. There's tons of warnings. The short of it is it's streaming through the entire data set and learning about all the statistics for, the standard deviation, all the like categories that are possible within a specific data set, and can actually present you with a schema and say, this is a numeric field, this is a string field, this is a date. These aren't always right, similar to Spark. When Spark does schema inference, it's not always right. You have to kind of eyeball it. Sometimes the data is messy, and strings end up in the number fields, and then Spark or TFX has to go with the lowest common denominator, which would be string. Generating statistics, validating. There's just kind of some sample things it could show. So, pretty powerful. Also, this sets up a baseline for the data set. So if we say today's data is the baseline, and from this point on, we want to detect skew. So if all of a sudden you start getting new categories that you hadn't seen before, or you have a bunch of zeros, like I said, these are things that you would want to know sooner than later. Okay. TFX transform is really just an abstraction for any kind of transformation that you want to apply. For the most part, these TensorFlow library, or these like TFX libraries, are TensorFlow specific. There's a project out of Amazon called DQ, D-E-E-Q-U, that does something very similar to TFX, but can actually do it on more data types or more data formats than just the TF record format. So DQ, yeah, Anshay can send the link to DQ. So yeah, DQ is can work with Parquet, which is very common. Our book is actually going to cover both TFX and DQ. There's some very interesting similarities and also differences between the two that we will highlight. So this is just generic transformations. Here's just a small sample. We're just normalizing data between 0 and 1, centering it around the mean. Here's some ugly Beam code that you have to debug if you want to continue with TFX. Hopefully they're cleaning that up. There's one other piece to TFX that is worth noting, which is the model analysis, so TFMA. So previously we did data validation, or where we were looking at the raw features. Now we can actually analyze the model after the model has been trained. And so this is very significant. This is the ability to detect bias. So every step of our pipeline, we want to keep analyzing what's going on. First look at our raw data, see if there's any anomalies, then we train the model, then we transform the model with the like TFX transform. Then we train the model using TensorFlow, using whatever, and then we want to analyze the model and take a look at different slices of data. Have we, so run all of the gender male, the gender female, or certain age groups, or certain times of the day, and see, is our model skewed or biased, or like, do we have enough information at all different parts of our data set? If not, we tend to have more samples during rush hour, for example, for a taxi data set, or for like Uber. They have lots of data during rush hour. They have so less data during off-peak hours. And that's where we would want to either balance or try to augment and add new data, or just collect like more data from those off-peak times if we can. Because otherwise our model learns where it has more data and could potentially be skewed towards those particular times of the day or those genders. Yes, as you see, there's a lot of TF record stuff here. This is great if you're using TensorFlow. This is absolutely horrible if you're not using TensorFlow. But for the most part, TFX is meant to support your like TensorFlow efforts. So not a big deal, since a lot of people do use TensorFlow, but just keep that in mind. So this can actually, in the Jupyter notebook, if it was working, it could actually render and show the different slices and let you drill in and actually analyze different times of the day, different genders, different whatevers. It gives you histograms. You can do, so there's a lot of code here. No mere mortal can actually create this code. You would have to start with somebody else's code. This is all written by Google folks who, have put these samples together. Okay, we're going to take a break here in a sec. TFX serving. So I think this sample actually works, right? Does TFX serving actually work? So TensorFlow serving is actually technically now part of TFX. TFX, by the way, stands for TensorFlow Extended, and really is, it's the whole ecosystem, not just TensorFlow, not just TensorFlow Serving. It also describes these like TFX components for the entire pipeline. So the like data validation, the model validation, and transform. All right, so we could actually run through this. What's happening here, I'm just going to run it just to get it all running, but what's happening here is we're training a model. So this is Fashion MNIST, the folks over at Zalando, I think, right?
Yep.
They got tired of samples using just MNIST, which is numbers between 0 and 9 handwritten digits, and they actually submitted this like data set as something kind of fun and different. So it's still 10 different classes, but now we have trousers and blouses and shoes and handbags and fun things. So we're training the model on these 10 different categories, same image size, 28 by 28. Creating a Keras model here, pretty small model, pretty thin, not too many layers, not too many parameters. If you're doing Keras, make sure that you're running model.summary. That'll build this nice little table here and tell you how many parameters. If you start seeing this parameter count like getting huge, that means you are like likely exploding this this particular graph, or this network way too large. Sometimes you need it, and then sometimes you just do it by accident. Okay, this is actually saving the model that we just trained. That it's using the save model format, which is now a standard for TensorFlow. And we're going to serve up this model. Oh, and then, here's a slick way. This is a CLI. There's also a Python way to do this, where you could display the signature of the model. And so this actually has the word, input image, and it tells you the shape, which is 28 by 28. And then tells you there's 10 classes that will come back. And that's going to be that's the confidence that it is one of those 10 classes. The -1, by the way, just means this could have many rows. So there could be many rows coming in, just like on the output, there could be many rows coming back. If we pass in 1,000, we will get 1,000 of these predictions back. All right, so this installed TensorFlow Serving, and started the server. So this is one of the images that looks like a dress. And okay, so passed one in here. This is an ankle boot, and it actually correctly predicted ankle boot. Okay, so here's the successful predictions, and that's using TensorFlow Serving. All right, I think we'll take a quick break, maybe 5 minutes here, come back at 12:01 p.m., and we'll take the final stretch home, which will be Kubeflow pipelines and hyperparameter tuning and a couple extras. So I'm going to answer questions for the next 5 minutes. See you in a bit. All right, so we got lots of good questions coming in here. Great questions. You guys seem to really be understanding what's going on and seem to know where the projects are going. KF Serving is the new standard for Kubeflow Serving. We actually don't have a complete end-to-end. At the very end, we'll be deploying to SageMaker instead of KF Serving. And we have to actually move over to use KF Serving. We were using Selden, and Selden broke something, and I didn't want to fix the Selden stuff. I would rather just move to KF Serving, which is the new standard, so that's the history there. I have to shut down the accounts at the end of I could probably keep them up until maybe 4 or 5, but after that I'd be violating my promise to Amazon, so they've already been generous enough to let us keep these up. I definitely cannot keep them up past today. Okay. Recommended way to handle batch scoring, batch requests to these endpoints. Yeah, so the end-to-end, the SageMaker example has a batch transfer, or has a batch prediction actually. So, and yeah, Kubeflow, I believe, actually Kubeflow does have an example that has batch transformations in it also. Yep. All right, so let me get back to this. Can it be KF to other things? Yes, so Kubeflow can deploy models to basically anywhere that has a target. You can, at the end of the day, you can put whatever you want into Kubeflow and just make sure it's a Docker image and it becomes a component inside of your Kubeflow pipeline. And I'll show you, I'll point you to how to create your own components. The Amazon folks have built their own components to talk to SageMaker, and that's what I'm going to demo today. So if we could talk to SageMaker, we could talk to anything, basically. Just as long as you handle all the security and all the authentication, and it's not just wide open. Okay, is there a plan to include workflow management, as was done before, a pipeline? Yeah, well, I'll probably bring Airflow back. We've been taking a look at step functions as well within Amazon. The Airflow stuff was nice and clean and actually did appeal to quite a bit of people. We were just trying to pare things down a bit. I also have been asked to bring back the MLflow stuff, which we're not doing today. So yeah, hoping to work those back in. All right, so I'm going to keep moving ahead. And let's look at Kubeflow pipelines. First things first, install the Kubeflow pipeline SDK. You might be able to actually pip install this now, but I like to keep all the versions stable within one workshop so that we don't introduce any bad things. We've already had enough bad things the last 24 hours with this workshop, so keeping it pretty straightforward. Okay, so what's happening here is we installed this Python library that's called KFP, and this stands for Kubeflow Pipeline. We've also, by doing the pip install, we now have something called DSL compile, which gives us command line capabilities to compile pipelines. And the term compile, of course, means take something human readable and put it into some format that can be executed by a machine, right? So that's what we will be doing here. We will annotate our code and make it so that the compiler can convert our code into a complete Kubeflow pipeline. So that's the whole context here. So I'll give you guys a couple minutes to read through this, but just let me explain. So here we're actually importing KFP. Here's just a regular Kubeflow function, Python function. We're using the DSL domain-specific language from Kubeflow pipeline, and we're actually creating what's called a container op. And so container ops, everything within Kubeflow, like I said, because it's based on Kubeflow, it's Kubeflow data, or it's based on Kubernetes, it's built on Kubernetes, it's Kubernetes native. therefore has to be a full Docker image and run in a Docker container. So that's why you see words like container op. And this is literally saying the base image for my Docker image, for the Docker image should be Python 368. Execute this command. At the end of the day, all that these containers are doing are just calling Python functions. And this is very, very simple. All this is doing, let's see, this is actually just writing stuff out here, I think. Think of how this is taking two numbers and then adding them. Where's the actual adding happening? Oh, right here. So this part right here, this seems kind of goofy because it's completely within a string. But this is, very, very primitive way to add two numbers and then store them in a file that could then get picked up by the next component. So the way that you pass data from one component to another is through the file system. So this is like a bit primitive. This is actually one area Kubeflow has been spending quite a bit of time on. I don't think it's going to get fixed for Kubeflow 1.0, which comes out next week or 2 weeks. But this is actively being worked on where this will become a little bit nicer. There's also something called Kubeflow artifacts, where you can keep track of the outputs and inputs, the outputs from every component, and then and similarly all the inputs for each component. And so this kind of stuff would get tracked. You could track the lineage and see how did we actually come to the answer. And so this is actually doing two sets of adds. It's creating a DAG. It's actually adding four numbers, but doing them in parallel. So first it's adding A and B. At the same time, it's adding C and D, and then we're going to reduce or then combine those two results and take the output of each and add those two numbers. All of that then so if you're familiar with Airflow, we're basically building up a similar kind of DAG, right? A directed acyclic graph of these operations. Here, we're just calculating things in parallel. So when we launch this, we'll go to the Kubeflow pipeline UI and see both of these happening in parallel and then both coming down to one single node to get added together. Okay, so if you notice, we actually annotate, or in Python terms, this is a decorator. Using that DSL, when we compile, we're giving it the name of this function, calculate sum, which conveniently has this particular annotation or this decorator. And this compile can go in and figure out what's happening here and build the DAG. And then ultimately, at the end of the day, did I run through? I haven't run through this yet. So let me. At the end of the day, we end up with a zip file there. We could actually unzip it. Unzip. And so we're just cracking this thing open just to show you what's, oops, sorry, cats. So this is the compiled Kubeflow pipeline. So here we see the parameters A, B, C, and D. We see we have calculate sum doing A and B. So the Kubeflow pipeline runtime knows how to read this compiled YAML file. And I've seen people actually writing these on their own or generating templates. Yeah, that's fine. At the end of the day, this thing has to be able to be read by Kubeflow pipelines. Here it's giving the Docker image that we told to use, and then a bunch of, here's MLmetrics.json for the person that was asking, how do I show metrics within Kubeflow pipelines? You use this file. And this is just a Kubeflow convention. You can actually rename it if you wanted to. You have to pass a special argument to say that you renamed it, so I wouldn't recommend it. But if you have the metrics that you're writing out, you have to declare them here, and then Kubeflow Pipeline UI knows how to render it. That's the closest thing that you'll get to something like SageMaker for the experiments.
And one question came just in, whether we can also pass the Python file as an argument?
Yes. I thought I had an example, I guess. Yeah, the question is, instead of compiling, calculate sum. Let's see. I don't know why you couldn't. All it's doing, honestly, we'll see it here, is it's literally grabbing the text. Which one? Oh, if you have a Python file, you can also try building using DSL. So here you could, back to that DSL thing. So pass to, yep, and that'll create it as well. So here we don't actually have the .py file because it's a notebook. But yes, if you had a .py file, good catch. Okay. At the end of the day, all this is doing, honestly, is slurping in the physical text that makes up this function and slams it into a Docker image and calls Python-C with this. Very, very, very primitive. It's a bit fragile. We'll see, I think, next where you could pass requirements TXT, similar to fairing. Okay, and then when all is said and done, we have that zip file. We're creating an experiment. We're just calling it AWS. We are creating a run that we're naming this. This could be named anything. And we're going to run that. So this is using the Kubeflow pipeline client. So this is part of the API from the pip install. And the cool thing is that this actually gives us deep links. So I can go click on this and look at the full experiments. Here I see it's running. Here I see the two sums happening in parallel. Looks like that one finished. This one's likely still running here. This one's still in the pending state, container creating. So by the way, the names of these, if I click on a component here, that name is physically the name of the pod that's running in the Kubernetes cluster, in your EKS cluster. So if you were to go to your command line through Jupyter and do a kubectl get pod, you would physically see this pod being executed. And these logs are what's coming out. Nothing too interesting there, but we see inputs and outputs. For artifacts, we should actually see, I think artifacts, we should have seen the file that was saved, but yeah, anyway, so these are the logs. If you did a print statement in your Python code, it would show up in this log. And in fact, I think number 3 might do it here, or I think echo actually does it. Yes, echo does an echo from the bash and shows up. So basically, anything that shows up in the container logs of your pod will show up here. And input 28, that was just an echo. For the calculate 3, which is taking the sum of the sums, we see the two sums coming in as input, and the output is 28. That gets passed to echo. And so this is all running on our Kubernetes cluster. All right, deep link to the specific run, which we got to through the experiment itself. All right, let's do one more, the SageMaker one. So now this is where we're going to cross worlds. We have a Kubeflow pipeline that can do certain things within our Kubernetes cluster, but can also call out to SageMaker. So this is where maybe we already have like an existing like Kubernetes cluster, but we realize we want to scale out, like burst out. Say that we have a super big event coming up. We have an on-prem Kubernetes cluster. We can't fulfill that like training run capacity with just our data center, so we have to go to the cloud. We can burst out and actually use SageMaker, a SageMaker cluster to do the training. And then all of this is part of one Kubeflow pipeline. So here we're going to install Boto 3, which gives us access to, so now, this is running inside of Kubeflow, which is running on top of EKS, which is backed by EC2 instances. So therefore, all of our Bodo commands work. I could get to my account. I can get all my IAM roles are still valid. And I could get to S3, install the Kubeflow, the KFP again. We didn't really, well, actually, yeah, this is a different notebook, so we have to do it again. And here we've got some special support for Kubeflow pipelines with AWS. Gives us the ability to create a secret. Now, this is probably one of the most critical. If you're going to really invest in Kubeflow, you need to understand these components. These things are kind of beastly if you look them up. So let's take a look. This would be, so this component was actually written by someone from Amazon that knows Kubeflow and knows the Amazon API, knows the specific SageMaker API. And you would have to do the same thing where you would understand Kubeflow, you would also understand your domain or your services, or your deployments, your cluster, and then be able to extend it. So this is where people that are really, really, really customizing pipelines and building their own pipelines, they're spending time here. So I'm going to grab one of these and just show you what is kind of going on. So, and what you do is make this public. Uh-oh. Yeah. You would make these public so that they could be referenced from your Kubeflow. Let me see, I lost my... From your actual Kubeflow code here. So we're going to build up this pipeline, and we're saying here's a training op, which is actually ends up being a Docker image. Here's a model op. Can't remember what that is. Oh, that's creating the model, and then deploying the model, and then doing a batch transformation. But again, this is all with SageMaker. There are certainly full examples of just using Kubeflow, but here I was showing kind of some of the flexibility where you can burst out into SageMaker. All right, so this is what it looks like. You would define one of these components, obviously give it sort of input, output, signature. So this is what you're expecting. Yes, anything that's working with Amazon typically requires the region, requires some Docker image ID, the number of instances, the type of instances, the volume size, and of course role for all of the unified security. Outputs, it's going to tell you where it trained the model. This is likely an S3 URL. And then also, it will generate a nice job name. If you're familiar with the SageMaker API, you know all of these already. These are parameters and the same outputs and the same parameters that SageMaker requires. This particular Docker image was created by a guy named Jeff Wen. You can Google this and work backwards from this particular image to figure out the actual Docker image that was involved. And at the end of the day, all it's doing is calling Python. This is what I was saying. It's not very exciting. It's just calling Python, and it's expecting there to be a train.py, and then all of these arguments. And this is the syntax that works within Kubeflow that has to match these inputs up here. And this is just a nice way for the Kubeflow UI to render what's required. So, for example, if I go back and look at one of these, I can click here, and I can see the input. So these are the inputs, and these are the outputs. And these directly come from those components. From that component YAML. Or we did it actually by just using annotations. Okay, so let's go back here. If we looked at a batch transformation one, or actually let's take a look at deploy. Deploy has been coming up here, so deploy is pretty straightforward. Which region, what's the model name? Once it's deployed, the output is the endpoint name, and here's the Docker image. Inside of this Docker image, if you went and tracked this down and found Jeff Wen's GitHub repo, you would see all it's doing is calling the SageMaker API beneath the covers. There's more native support coming as full Kubeflow operators that will make this component creation even easier. But for now, that's so that demonstrates how you can call basically any API from these Kubeflow components. Okay, so let's keep going. Okay, one little trick here. For this to work, you have to make sure that you change this role. So obviously, if you see XX, that is not a valid role. So the way to get around this, go to the SageMaker console. Go to notebook instances. And all we're doing is just looking for the ARN that we've given full access to. Is it this one, Hunter?
Isn't it the model endpoint?
Which one?
Which step are you in? If you go to...
That was a service role. Which one? Yeah, one sec. I think it's...
Can you give me the step?
What's up?
Which step are you in?
I'm trying to get the ARN for SageMaker execution role from the. I think it's the same one. Yeah.
Yeah, that's the IAM role. Go down. Yeah.
Okay, so grab this one, which should be something like team role, something, something. Yeah, it was different yesterday because we used that role. Yep. And paste that in here. So again, go to SageMaker, go to notebook instances, go to team role, and then just right-click that, and go back to your notebook, paste that in, and then this all should work. So the region's the same, image ID, this is a public image. Or no, this is actually the image. Is this a public image, or is this one that this must be a public image?
Yeah, that's the public one.
Yeah, it's this one here. It's a public image. Okay. Yep, there's a k-means one. All right, and just run it. And so basically, what we're doing is we're dynamically creating a pipeline using the DSL. We're creating a SageMaker training op, which, if you remember, was actually defined up here. So these are all the 4 ops that we can run within our pipeline, and they've been defined by somebody else, or could be defined by you, and you would point to your YAML for like your components, and now we can make those part of a Kubeflow pipeline. So the first step is training. The next step, and we actually created a secret as one of our blobs of instructions in anticipation that we were going to do this. So there's now a secret that we could just, and this is a secret that's been created within the like Kubeflow cluster. So within EKS, so Kubernetes has a concept called secrets, and you can create a secret. And in theory, if you're not an admin, you can't see the secret, but you can refer to it. And so we're not actually putting in an access key here, but we're saying use the secret that was created by the ops folks, which was us when we installed Kubeflow earlier, and use the value of this key and the value of this key. And by key, I mean key value pair. All right, so here it's doing a training op. Here it's doing create the model. Here it's deploying the model. And here it's doing a batch transformation. So let's run through this. Create that pipeline, compile it. We could crack it open, but yeah, let me launch it here first. Let's take a look at what it looks like. unzip and cat. It'll probably just be pipeline.yaml. No? Okay, something I can't seem to figure out. Let me rm pipeline.yaml. Okay, so here is the compiled. So this is a fairly complex workflow or like pipeline. But really, it's just complex in that it's using somebody else's pipeline like components, which was built by Amazon. You give it the instance type, you give it the instance count, saying 2, here's the S3 bucket, and everything should then fall into place. So we have the experiment link. Let's go take a look there. Go into that. Take a look. We can look at the logs. Here we actually see the logs. This component is calling the SageMaker API. It submitted a training job. Now we should be able to go to SageMaker, look at the training jobs, and eventually, oh, actually we see it right here. This is the exact job that we launched from our Kubeflow pipeline. Here's the k-means. That's the training image that's used. Here's the instance type that we specified, instance count. These are the metrics that are going to be scraped using this like regex from the Docker console that's actually running all of. So each of these instances is running a Docker container with this model being trained, and it's spitting out these metrics, and we're capturing them and can now post these to CloudWatch. So these become first-class metrics within CloudWatch that you can build alerts off of, that you could build dashboards from. Here's where the model will go when it's complete. So this will actually be one of the output parameters. Here's the hyperparameters. These are also being logged, so you could build dashboards and look at and then compare. Here we can look at the algorithm metrics. We could look at the logs. We could look at the instance metrics, CPU, GPU load, training progress, training MSD. Okay, so we'll have to let that run for a bit for that to complete. Hopefully you guys got there. Let's see, are we at a point to take a break? Are there questions?
Yeah, let's maybe do a quick break.
Okay, yeah, quick break to answer questions and yeah, get everyone up to speed here, and then we will, once this is actually deployed, we'll actually be able to make these predictions. And I think last night this took 5 or 10 minutes, maybe 10, 15 minutes.
Yep.
Yeah, probably 10, 15 minutes. So why don't we come back in 15 minutes at 12:46, and I will answer questions as much as I can. See you in a bit. Okay, so I think mine just deployed. I answered a bunch of questions. Hopefully you guys figured out the right ARN. It's back on this page. Under SageMaker, notebook instances, click into workshop. It's this ARN down here. Okay. And so mine deployed, lucky me. If we click in here, we could look at the logs. We see, so this is the actual S3 location of the trained model. We can compare it to, if we go over here, go to training jobs. Should be the same S3 location. Right there. K-means example model. K-means example model. And then this is like the job name. And then it's typically, yes, almost always it's output/model.tar.gz. Click into this. What was this next one? Looks like it is creating the model. This one deployed it. Endpoint is in service. This did a batch transformation. So all of these show up as first-class citizens within. So here's batch transform jobs right there. Here's the endpoint. I'm going to grab this name. This looks like it's in service. So I should be able to go back and plunk that into here. And the first one takes a while. The next couple should be a little bit quicker. That one's not that much quicker, but yeah. So we deployed the model. We used SageMaker. We could scale it out. We could add, many more instances here. We could do A/B tests. You can update the endpoint. You could do A/B tests. You could actually run multiple models on a single instance in what's called multi-model inference. And I've been seeing some work being done on ensembles and more complex ways. So to me, this is actually a pretty nice way to deploy the models, and then I could scale them out with the rest of my infrastructure versus having a separate EKS cluster for serving, which you typically want to do. You don't want to mix or use the same exact Kubernetes cluster for training and for serving. These are different workloads, different resource utilization like characteristics. So, all right. And so let's jump into the next one here, distributed training, and then we'll show some Kubeflow metadata tracking, and we'll do Kubeflow hyperparameter tuning, neural architecture search. I'll show you guys how to convert a model down into from TensorFlow down into what's called TFLite, and we'll actually get some pretty big performance gains. And then just a fun little one, something I think is actually pretty important is differential privacy. This is something you want to pay attention to if you're not familiar with it. So we'll talk about it here in a bit. Let's go to distributed training. So here with, and I think, Anja, talked about a lot of this. There's something called model parallelism, and there's something called data parallelism. Most of us are probably familiar with what's called data parallelism, and that's how Spark works. This is where we're actually dividing up the problem, or we're actually dividing up the data and applying the same problem. Or that doesn't make any sense. But we're like splitting up the data and doing the same processing on those separate batches of data in parallel. With model parallelism, we're actually splitting up the problem across different nodes. So classic type of example would be like Facebook. They have very, very large graphs of people. They can't fit them all onto one single node. So when they're doing graph analytics and graph recommendations and graph similarities, they have to split it up. There's no one single pathway, or there is not one single node that could hold that much data. So they have to split it up, split that problem across multiple nodes. Model parallelism is not common unless you have tons and tons of data and cannot fit into those GPUs or those nodes. So most of us are more familiar with what's called data parallelism, and this is where we're splitting up the data and basically applying the same processing to each mini batch of data, and then collecting all that data into one. So Antje talked about this earlier with synchronous and then asynchronous. There's also some goofy names for these, in-graph replication and between-graph. I always forget which one's which, but yeah, one of them is model parallel, and the other one is data parallel. This is just what Google just happened to be calling it, that nobody else in the world called it except Google. So these terms have stuck, but mainly because of Google. Okay, and so let's just launch a job here. So let's first take a look at what's in here. This is something called TF job. This is what's called a custom resource definition. And TF job we had introduced during installation of Kubeflow. We told Kubernetes that you now have something called TF job, and we can now do kubectl space get space TF job and look at all TF jobs. Now Kubernetes knows what a TF job is, and this is TensorFlow job. There's also PyTorch job, there's MXNet job, there's MPI job. And so here's the actual Docker image. This is a public Docker image that's been pre-built that has MNIST, meant for distributed TensorFlow. And there's another one here. We're saying we want 2 replicas of the parameter server. So parameter server so this is required. If you see in this data parallelism, there's this PS cluster over here. So we're actually asking for 2 of these. This shows 3, but we're actually asking for 2. And this is what's collecting all the data from each of these separate workers. And then we should have a separate number for the workers. We want 4 workers. So all of this will get, all of this gets distributed to our Kubernetes cluster, and then Kubernetes figures out where to place these pods or these Docker containers, and then they all will work together to solve this problem. So let's actually create it. And then, so now we could say kubectl get TF job. Instead of looking at the pods, which we also could do, and we see all these pods got created, there should be 6. There's 2 parameter servers, and there's 4 workers. But instead, I could say, get me TF job, and kubectl actually knows about it now. I can say, describe the job. This will give me, it's telling me that the job has been created, that the job is running, successful. If I want to look at just, so I could do get pod, but also grep it and just show the distributed TensorFlow ones. And then if I want to actually look at the logs of a single worker, so typically worker 0, by the way, is given special privileges and special duties. This is just the TensorFlow thing, distributed TensorFlow thing. You are always guaranteed that there's going to be worker 0, so you could check for this inside of code and say, if I am worker 0, then it's my job to keep an eye on the parameter servers, make sure they have not crashed. If a parameter server dies, that's bad. You have to stop training until the parameter server comes back online and somehow gets restored. If it can't get restored, then all training has to stop. Also, worker 0 has special duties in that it's going to be writing checkpoints, or it will tell these parameter servers when to write the checkpoints. It's also collecting information from all the workers and writing it out so that Tensor board can actually render and show the results during training. Here's a PyTorch job. So again, this is PyTorch job, same exact thing in concept. Just know that PyTorch is from Facebook, and Facebook has something called Gloo, G-L-O-O. If you're familiar with TensorFlow and Google, you know gRPC is what Google prefers. Facebook has this project called Gloo that I had never heard of before I saw this example, probably last year. But this is their gRPC, basically. This is their node communication mechanism. Same thing, we're giving it a Docker image that has PyTorch installed, has the train.py all built in, and so let's run it. Now we can do describe PyTorch job, show us what's going on, creating. So here we have 2 masters and 2 workers, or no, sorry, we have 1 master and 2 workers. And there's really no reason why we did that, except that's just how this example was set up, 1 master, 2 workers. Okay, still waiting for, once the master comes up, we could take a look. But yeah, this is actually downloading all the images, which sometimes takes a while. Okay, so that was PyTorch, and that was distributed TensorFlow. Any questions coming out of that?
Yeah, so there's one question. How does EKS know that I want to run the distributed job on a specific type of instance?
Yeah, so great question, of course. How this works is you can, so typically you can tell it, so this is really more of a Kubernetes thing, so that's good that you knew to call out as EKS specifically. Inside of my YAML, I could actually tell it which, so what you would do would be label your nodes, so the actual instances. If they have a GPU, you would put GPU and maybe the type of GPU. Because just getting to a GPU might not be good enough. Maybe you want the Volta V100 because this particular workload can take advantage of the tensor cores or whatever specific. And so what we see people do is they label each instance, and then when you build your YAML, you actually put in there, I want to be placed on a node that supports the Volta V100. So you would have to build that into your YAML. There's really no good way to create this YAML, by the way. People just literally use projects like Jinja, Jinja, which can do templating for Python, and can create YAML and fill it in. And yeah, but you would use Kubernetes labels, they're called, and then when the Kubernetes scheduler is trying to find a node to place that pod onto for execution, it would place it based on those label selectors, they're called. And so good question, because typically your parameter servers are just simple CPUs. You don't need GPUs for these parameter servers. In fact, you want higher memory and less compute for those. If you had to make a trade-off, you would choose higher memory because you are storing more things in memory, and you're just doing simple additions or simple reductions, whereas your actual workers are the real workhorses and need those GPUs. Anything else on that one?
No, I think that's more.
Okay, so let me keep going here. We'll get to metadata tracking. So similar, this is pip install kf. So similar to KFP, we have KFMD. KFMD is KF metadata. What we're doing here is showing an example of how we can track the lineage of our pipeline. So as the pipeline is going along, there's inputs that are coming into each node that we saw within Kubeflow pipelines. We do some processing, then we output something. And these are called artifacts. And we want to track that lineage. The most obvious examples are we have raw data coming in. Maybe what we're going to track is the S3 bucket where that data came in, or the Kinesis stream where that data came in, something. And then we do some processing, and then we output some data. So let's say we're outputting that data to S3. And we've transformed that data somehow. We've done feature engineering. We've taken CSVs, we've converted it into Parquet. So show us those two, so those two buckets within S3. And we could track that on a per pipeline basis. So we could see, where did this data come from? What transformations were done? Where is the data? So I could go back and actually track it. And then the next step, of course, would be training the model. So we have engineered features coming in, let's say Parquet or like TF record format, something. And now we have a model that like comes out. And for batch predictions, we have that raw like data coming in for the prediction, and then all those predictions coming out. So all of that would get tracked. So this is actually like a really silly example. It's just hard-coded. But once we load it up here with data, here we could actually use the Python API, the KFMD API, to list it out and show it right here. Or, even more exciting, so here's metadata run. This is tracking the run, execution. So this is really simulating what can be done here. We could even track like the query that was used to generate that data. And now we can go into artifacts. So go back to Kubeflow, go to this little hamburger here, go to artifact store. So find the goofy Istio system like URL that was generated when we installed Kubeflow, and go to artifact store. And all of these were fake generated just now. But the cool thing is that this has this concept of a type. So this is a data set. These are some of the metrics that were saved as part of this pipeline, and these are the actual models. And we could track versions. There's not, it's very bare bones right now, but there is a lot of work going into this. Okay, so that's metadata. Anything in there?
Yes, is the metadata captured automatically?
So let's go back to the example. It is not. You actually have to actively make these calls. My guess is they, at some point, will start to make this easier. Instead of making calls like this, you would just annotate or add a decorator or something like that. But the short answer is no. You have to explicitly track these. Okay, hyperparameter tuning. This is the concept of, we know what model we're trying to train. We've already chosen it. Maybe it's XGBoost. Maybe it's convolutional neural network. But we don't quite know which hyperparameters we should use for our algorithm. So this is actually one step kind of more primitive than something called AutoML. Which actually is where you just point to your data set and then let AutoML figure it out. In SageMaker land, this is called Autopilot. And then Google Cloud also has something just called AutoML. This is not that. This is just hyperparameter tuning. Kubeflow does not support the AutoML. It supports hyperparameter tuning. It supports neural architecture search, which is a little bit closer, but really, that term AutoML is the most basic. I point to my data set, I tell it what I'm trying to learn, and I let that mechanism do all the hyperparameter tuning, do all the algorithm selection, and spit it out. This is just hyperparameter tuning. I've already chosen my model, my specific algorithm. Now I want to find my hyperparameters. They're called hyperparameters because in normal model training, we're learning parameters. In hyperparameter tuning, we're actually learning the hyperparameters on how to learn those parameters. So Kati is the project name based on Google Vizier. So this was pulled in. And here's another example where we have some kind of goofy YAML. This is just the Kubeflow spec on how to do this. What we're typically doing is giving it the parameter that we're trying to learn. This is called learning rate. This is popular for gradient descent-based optimizers. There's SGD, stochastic gradient descent. Here's a couple other optimizers that use this hyperparameter called learning rate. We tell it the range that we want to explore. The number of layers also. This is how deep is our neural network. This is a valid hyperparameter. The deeper the network, the more combinations of previous layers you could try. So if you think of the neural network kind of left to right, If we have deeper neural network going from the left to the right, I could actually try more combinations the deeper I go of all the different parameters that I'm learning, because all these are in like most cases fully connected or somehow connected to each other. These layers are all connected. If I go wider, meaning I have less layers but wider, more parameters per layer, that's still pretty good, and certain data sets do benefit from that, but just know that you're not like letting the neural network explore all these different combinations that you haven't thought of yet. All right, so we launched one. Oh, and there's these different strategies for hyperparameter tuning called grid search. That's where we explore all the different combinations of 0.01 to 0.03 combined with 2 to 5. So we're starting to get into combinatorics here. And there's huge explosion. Every new parameter that you add, yeah, this goes up. So yeah, so keep that in mind. You could also do random search, which is, if you think of grid search being the slow or the most complete search through the space, but also takes the longest, we could also do random search, which will randomly choose. And there's some thought that that's good, that randomly we can usually get to what we're looking for. People that are OCD like me, they want to know that we've explored all the different combinations, and I would actually go back to grid search. And if I use Amazon, I could scale this up. If I use Google, I could scale this up. Run all these in parallel. Yeah, it might cost a few more cents, but I know that I've explored the entire space. There's also something called Bayesian optimization, very popular, where as we're exploring the space, we're able to whittle away combinations that don't make sense, where there's very low probability that could be the right answer or the best hyperparameter set. And yeah, there's a bunch of other strategies as well too, but yeah, Bayesian, grid search, random search are the big ones. And the cool thing is all I have to do is make one change to my, actually not catting this here. Yeah, let me cat this. I just have to make one change to my YAML and it will explore. So this is algorithm. So this is how are we going to learn and do our hyperparameter tuning. So I could change that to grid, I could change it to Bayesian, and boom, I've got a completely different strategy to learn these hyperparameters.
Quick question on that one. Can I actually add my own optimizer?
Your own strategy, you mean? So you want to add like another, like your custom, my special custom search. Absolutely. Oops, I have no idea what I just hit. Yes, you can add your own hyperparameter optimizer, yes. And in fact, these are all open source. So you can go, if you click into the Kati project and search for grid.
So for example, yeah, Jaime just shares the particle swarm optimization.
Yeah, exactly. Yep. Grid search, let's see, grid. You would go in here and implement the, let's see, this is not what I'm looking for. Implement, yeah. So there's a bunch of like base classes that you would implement. Yep, yeah, base interfaces.
Can you think of where this would be used in inference / production?
Yeah, and this is something my previous company was exploring, which is kind of whole pipeline, like hyperparameter tuning. So not only looking at the offline metrics like we're looking at here, which is accuracy of our model, but also taking into account the latency of our model, the size of our model. I haven't seen people do this much. People have like written about this concept. It's something we're actually talking about for the book as well too. Probably not a lot of people thinking about that stuff, but yeah, it is a pretty good And so basically, instead of optimizing, so here I have to say what I'm trying to optimize. Here I say I'm trying to get to 0.99 for my validation accuracy. I'm trying to maximize this because this is accuracy. If it was loss, I would try to minimize. Also, by the way, the 0.99, if we hit 0.99, it will early stop and not have to run more because it already found and reached the goal. But yeah, you would essentially have to build in your own objective metric and then extend this out into production and have the feedback mechanism. When we tried to implement this at my previous company, there were so many moving parts that it wasn't really tractable. It was difficult to reason through. But yeah, definitely very interesting for people that are concerned about model size and then performance online. All right, so we should be able to get, at some point, we will get to, here's Bayesian optimization. Here's another one called hyperband, which is a form of, or it's kind of similar in theory to Bayesian. It's like whittling away possible combinations and trying to lower or like reduce the overall space that needs to be explored. Let's go to hamburger land here, go to Khatib. So these are the different examples that we've done. We were trying to figure out, I think they changed some stuff. Let's see. We're supposed to be able to go look and compare these. I couldn't quite find it. There's a screen that looks very similar. I'm glad we have the screenshots, but there's a way to compare these. And this is something called a parallel coordinate plot. And this is a way to look at all of the hyperparameters. So we have learning rate, we have num layers, and optimizer on the right. And on the left, we have validation accuracy and then accuracy. And we can kind of, starting from the metric that we're trying to optimize, we can back into which of these hyperparameters and the actual values. So it's a way to work backwards from the metric that we're trying to optimize back into the hyperparameters that were used. That's a nice way to visualize that. Yep.
And there's a really interesting question coming in. What are the differences between Khatib and Keras tuner?
Oh yeah, Keras tuner. Yeah. In fact, I used to have Keras tuner in the workshop. It was a little bit wonky. It works pretty well. Keras tuner is not integrated into Kubeflow at all. You would just run Keras tuner in your notebook. I don't know how to distribute Keras tuner. I don't know how to do, 5,000 combinations at the same time in parallel. As far as I could tell, it was kind of doing it just using, primitive Python threading and yeah. So I guess the summary there is I don't know how to scale Keras tuner outside of the notebook, and it's certainly not integrated. But at the end of the day, they're all doing the same thing, which is trying to optimize some metric that you give it. Also, I don't know if Keras tuner is actually part of Keras or if it's just like a side project off the Keras repo. The last I checked, it was not part of Keras, but maybe it is now. All right, neural architecture search. So this is so there's some differences. There's some subtle differences here between NAS and hyperparameter tuning and then AutoML. Let's see. Let's actually run one of these. Yes, in concept here though, I can. I'm still optimizing for some metric, and I'm trying to figure out what's the best architecture that should be used. Is it convolutional? Is it recurrent? What are the sizes of the network? All right. So I think I can let you guys read more about that. I think I want to get to TFLite, and then, because we're kind of over time in terms of lunch, and then I think that'll actually wrap it up. So we kind of powered right through lunch. Oops, all right. Okay, so I'm going to show you guys a quick, just a super basic TensorFlow model, just to give you an example of what's possible here with this project called TFLite. Now, TFLite was sort of initially built for smaller devices. I'm seeing more and more people use it for the data center as well. Certainly, the concepts are much more commonplace now than they were even 1 or 2 years ago. The idea here is we train a model, we save it, we can visualize it. This is kind of fun. So that's our graph. Now this contains, so the context here is we're now preparing to deploy this model into production. And if we just look at the raw graph, there's lots and lots of nodes here there's parts of this graph that are not needed when we do predictions. And so some of this, actually most of this is actually stripped out now by TensorFlow. It didn't used to be, but let's strip it out here. Also, take a look at the size of, so we have a graph that's 12K, so that's the actual graph itself. When we froze the graph and actually got it down to 392 bytes. So we stripped out all of the stuff that's not needed and just got the raw like prediction graph, and now we can, this one's a little bit lighter. Actually, it doesn't look that much lighter. Anyway, yes, let's keep going here. I'm just going to show you. Okay. Okay, so here's our model without much being done to it. It's a 20K model, and now let's show it. This is the same thing that I showed earlier, where we can display the signature. So this is just taking X. So this is just simple Y equals X plus B. And let's make a prediction. 5 milliseconds. Okay, that was a good prediction. 5 milliseconds seems reasonable. Now let's convert it down to TensorFlow Lite. So TensorFlow Lite is an alternate runtime that's much, much smaller than full TensorFlow. So TensorFlow runtime by itself, I believe, is maybe 70 meg, maybe 80 meg, maybe it's even higher now. And we want to minimize both the runtime and the size of the model so that we can, A, speed up these predictions, and B, fit these onto smaller devices. So TensorFlow, this used to actually be called TensorFlow Mobile. I think, maybe 3 years ago. They switched it over to TFLite to be more generic. So I'm actually taking that model and I'm processing it, and I've actually reduced it from, what was it up here, 20K? Yeah, so 20K down to 600 bytes, 656 bytes. And I've still preserved it, so this actually scanned it. It looked from start to finish what is the bare bones that's needed to make this prediction happen, and there's really nothing that's needed except the add operation and the multiply operation, or the, add and the multiply. All right, so let's look at this. Here's 656. It's in this TFLite format now. So there's obviously this alternate runtime called TFLite. And yeah, this is part of TensorFlow 2.0 as well too. Slightly different way to invoke it, that's fine. Let's take a look at this is 20, what is that, microseconds versus 5 milliseconds. So huge performance gain. Yeah, obviously, did we lose any accuracy with this model? This is something that is also part of the hyperparameter tuning. the full complete pipeline for hyperparameter tuning. If you were really not just looking at performance like latency, you would also look at the size of the model as well. And then also accuracy. Yes, how much accuracy did you lose? How much are you willing to lose by saving on space? Okay. All right, last concept here is differential privacy. And then we'll answer the final questions and probably wrap up in about 10 minutes here. So differential privacy, very important concept, was made famous by Apple a few years ago during the WWDC developer conference. They came out and said that they're using this concept, this mathematical concept called differential privacy on each of the iPhones, and in this federated manner. So data is basically masked. Masked is kind of like an understatement here, but it's sort of an oversimplification of what's happening, but it's the ability to learn from our data, but not be able to get back to the specific data. So by using differential privacy, we're kind of blurring the data, but we could still learn patterns, but we can't get back to the exact data. So once that data leaves the phone, you cannot trace it back to the person, but we could still learn the patterns, at a larger scale. So what we have is something called a privacy budget. If you talk to the lawyers and you ask them how much budget you're willing to give, you would, so they would want 100% privacy. If you talk to the data scientists that are trying to learn about the about the users, about people's behaviors, they're going to want no privacy and they want more data. More uniquely identifiable data. So there's this budget that you provide. I want 50% privacy, and there's this natural natural way to balance accuracy, your latency for your predictions, and your privacy for your source data. Okay, so there's this project within TensorFlow called privacy. So you do pip install TensorFlow privacy. And suddenly you can you actually wrap your current optimizer, which is, in our case, stochastic gradient descent. So here's the traditional optimizer, which is gradient descent optimizer. You wrap it in what's called the data privacy optimizer. And now this thing can take into account, as it's training, it's sort of masking the data. So you don't have to purposely go in and, get rid of credit card numbers, get rid of addresses, get rid of whatever. You could still keep that in there, but we're training on kind of a blurred version of it. And so the more private you are, the less accurate the model will be, but that's where you have to find the balance. So you can run this, and it should end up in, oops, I didn't run the first cell. Oops, I didn't run the first couple cells, because we can't rerun this here. So yeah, very important concept, and yeah, definitely worth keeping in mind if you are working with sensitive data. I know folks like Intuit, the TurboTax people, they've been very outspoken about their use of differential privacy. They're also exploring other ways to train on sensitive data, but preserve as much as they can. The problem is if you start masking out super important details about someone, like their zip code or their preferences in certain things, you now lose the ability to personalize and learn from your users. So you have to find a good balance there. Okay, I think that about covers it. Anything left in the instructions? There's no cleanup that you have to do because we're just going to tear these down, so don't worry about that. We'll leave this up. It's about 1:30 right now. We'll leave this up till 4:30 probably.
Sounds about good.
4:30. Okay. And if you have questions, let us know. Answer questions for the next 5 minutes.
Yep. So maybe want to share. There was fun follow-up questions when we ran through the metadata tracking.
Okay.
how to add hashes to represent data sets used, or in other words, how do you recommend like tracking the states and changes in data sets?
Yeah, the way it's being done brute force right now is just different S3 buckets. And I mean, even talking to like Google people that have had this problem for years, yeah, all they do is just create a new prefix within Google Cloud Storage and copy the data over there that has the slight differences. It's a very, very common ask. There's tools like Pachyderm, which has a little bit of integration with Kubeflow. And I believe there's some like efforts underway to help with the versioning. I don't know how much Pachyderm is actually part of those, but yeah, the ability to like version data. We've seen people use S3 bucket versioning for this kind of thing. Oh. Yeah, that's a tough one. Yeah, any other questions? Yeah, did you guys find that useful? Maybe we could put the link in for the book one more time, and then, yeah, let me check here.
So if you have more questions, put them in the chat. We're going to answer more questions right now. We're still here for a little bit of time. So if you have questions that haven't been answered yet, just repost to the chat.
Okay, Verada, looks like you didn't potentially install the, okay, KFMD. Yeah, I'm not sure what's going on. Yeah, like you've been having some problems with the installations. From Kati, let's see whether there's, okay, from Kati. So I guess one of the questions is, why would we not do hyperparameter tuning for all models? Yeah, I would definitely recommend that, especially because especially with neural networks, there's so many different types of things you can tune, like the number of parameters per layer, of nodes per layer, the number of layers, and the way that they're connected as well. I don't know if we have the SageMaker AutoML demo ready, but basically, with SageMaker AutoML, it's even easier. You actually point to your data set. Yeah, let me see if I can find it. Let me share, grab the share here. So here's an example where we actually pointed to a data set, told it what to, told AutoML, or yeah, told this like product called Autopilot. Yeah, and then Autopilot is free. You just pay for the compute, so there's no extra charge as far as I know. I can't remember actually. But here I pointed to this data set, and this is a data set about some kind of marketing data set. It figured out that the column that we're trying to train is either yes or no. This was automatically generated, by the way. This is white box like AutoML. So this is, we point to this data set. The data set recognized there's 39,000 rows. The column you're asking us to learn has only 2 potential values, yes and no. The whole data set has 21 columns. We recognize this as binary classification. And then it's actually telling us different like metrics. So if you remember TFX for data validation highlighted things like the number of missing values, all the metrics about, like number of uniques, descriptive statistics, so the mean, the median, min, max for the different values for these different columns. So that's one thing, that's the exploration. This was automatically generated by Autopilot and was presented to us in a IPython notebook that we can modify or share. And by the way, this is all part of our book. That's where like a lot of these notebooks come from. And then this was also generated and this is actually highlighting the top 10 candidates that were found. So here it's saying we think XGBoost would be good, and here's a bunch of feature transformation scripts. And all these scripts are generated for us, the .py files, and so we could use this during training and during prediction also. So these are the top, so it's not just what's the actual algorithm, this is also showing us what's the feature engineering that's required. So this is using PCA. This is all Scikit-Learn code. And then XGBoost. But all these transformations are all standard Python, standard Scikit-Learn. Here it's doing one-hot encoding. And so given the type of data, so if you're familiar with a product called Data Robot, yeah, so Data Robot has something like this, where you can point to your data set and let it take over and like do the rest. So pretty cool stuff. Yeah, Autopilot, you can tell it how many of these explorations to do. So keep in mind that the autopilot is not just choosing hyperparameters, it's also choosing the actual algorithm. And with like autopilot, this is actually choosing and like generating the feature engineering scripts that are needed for both inference and for training. So that'll take the raw CSVs and convert them into the numeric data that's needed by these models. All right, a couple more questions. Yeah, Delta Lake, yeah, very interesting project. I actually used to work for Databricks. Yeah, very interesting project. I don't have much material on it. Seems pretty interesting, though, to kind of combine streaming and then sort of incremental updates. Okay. Oh, yeah, so Jamie's asking, why not use TFLite for all models? It would save cost, and you can tune the losses. Yeah. I spoke with lots of people, especially with my previous company, about how to optimize and at like what point. People didn't even think about TFLite to use in the data center. They just always thought it was a mobile thing, and then people were actually using it. So the certain models will benefit from the types of things that TFLite does. So TFLite is quantizing down from 32-bit down to 16-bit. You can actually do tricks during training that help out the quantization later, or that minimize the accuracy loss. Let's see. Yeah, all the notebooks are out there, all the code. Dawn Songs Group, and just came up with massing. No one else can. Oh, okay, cool. Can autopilot be used for multi-step time series predictions? I don't think so, not right now. The question is about autopilot and time series predictions. I haven't seen any examples. For the most part, the version that was released, so that feature was just released at like reInvent back in December. There's a lot of engineers that are focused on that within Amazon, and I'm, fairly certain that that time series will pop up. Right now, it's mostly supervised classification and like regression type workloads. Use autopilot be controlled? Yeah, the autopilot. How is autopilot built? Is it per second or is it per hour?
It's execution time. Yeah, I'm just looking it up in the developer guide. Yeah,
they show it like per second. I thought for the most part, wasn't all of EC2 now billable by second and not by hour? Billable seconds we saw earlier. Yeah. Yeah, Dean, we're looking that up right now. SageMaker example for the REST API. Yeah, we actually did that. Actually, there's like lots of examples for SageMaker REST API. Let me just do a quick. There's an actual tutorial on how to build. So here's Amazon SageMaker examples. Here's like bring your own XGBoost, for example. Yeah. Let's see here. Yeah, lots of good examples here. Typically, oh, and the Docker images are all open source, by the way. So that's kind of bring your own XGBoost, SageMaker. I think I might have sent this earlier as well too, but you can get to, oops, I didn't send it to everyone. Yeah, Jamie's asking, can we give it like a fixed number? I have $1,000 to spend on this. Yeah, I'm trying to think. I don't think you can put in a dollar amount, but I guess you can back into that number if you know the instance type that you're using. And then, can you do it by time? Can you say train for only?
You specify basically how long every job has a maximum runtime in the whole thing.
Oh,
it's
yeah,
runtime
yeah.
based. It's not instance or dollar based.
Yeah, there's a parameter that you pass into all of SageMaker basically, yes, including, no, is it just autopilot? Yeah. You could say how long you want this to train for and then stop after that. So that's a way to get to the dollar number. Yes, Algorithmia, a good company, based here in Seattle actually. Oh yeah, yeah. So Radha suggested set a CloudWatch alert on the cost. Yep, can do that. Okay, there's not really a Slack channel. I think I still have the Pipeline AI Slack channel running, but not too much activity over there. But if you guys have questions, beyond today, please email support@pipeline.ai. And Ancha and I had a blast. Check out the book when it's available. We're going to have streaming stuff in there as well too, so how to do basically like a Delta Lake kind of thing. Okay, and yeah, the billable stuff we're trying to Google for. Did we find anything? But yeah, we have to Google around for that. So, okay, thanks a lot, guys. If you have any other questions, just ping us at support@pipeline.ai.
Thanks so much.
Thank you.